All right. Well, I have started working on your first homework assignment. It'll be due next Thursday. I'm going to finish it tonight when I get home. Put some more questions on there from Chapter 3. There are going to be, I'm not sure how it's going to work because this is my first time putting together quizzes of this sort through D2L. So some of them are going to be multiple choice, there's going to be some true-false. Unfortunately, with a lot of math problems, there's one of two ways to do it. It's either I give you 4 answers for multiple choice that are variants of errors that I think that you might make, or I just leave you with the space to let you fill in the number that you think is the right answer. Now, anytime that there's going to be a short answer like that, so if there's anything on the quiz that's not either true, false, or multiple choice or matching, in other words, if there is possibility that your answer might be correct but might not be auto-graded as correct, right? So I'm going to try and come up with things like really common alternative answer type stuff for some of those, like put in your mathematical answer here. But I'm just telling you that D2L is going to grade it for you, or at least give you a grade. It will try to auto-grade it. If there are things like that, if you go back and look and you got those wrong, I will go in and manually double check those to make sure that you didn't put an answer in there that is technically correct and I just didn't think of it to tell the machine first, right? So, so that's the way that's going to work.
Just to clarify, are you talking about homework?
Homework, yes.
But it's a quiz? Like the homework is a quiz?
The homework
like
is a quiz.
Okay.
That you will do online, yes.
And
so,
it's like timed like a test?
No.
Okay, okay.
No. It's submit once, so it's not like do it as many times until you get an A. But it is, get together with friends, work on it, whatever, submit one type of thing. Okay. So it's a quiz that you can open as many times as you want, but that's because on D2L, everything is a quiz. It's either a quiz or a survey, and since I need you to be graded, it can't be a survey. So even the exams will be quizzes, they'll just be big ones that actually do cut you off.
Okay.
Are the quizzes like the exams when it comes to questioning, like my question will be different than her question?
No.
Okay.
Homeworks, okay, it's going to be a quiz, but it's the homework. And it's going to be titled homework number 1, homework week 1, all right? So when it goes live, which should happen tomorrow morning, you'll see it, you'll click on it, you can open it up, you can do it. It will be due next Thursday. You'll have as many times as you want to take a look at it between now and then, check your answers, whatever, what have you, maybe work with friends. This is homework. It is a 1/5 of your grade, a little bit less since I'm going to give you one for free as long as you do all of them, right? So I would advise you to double check things, right? Like not necessarily double check them with me in class because I'm not going to work through your homework in class. We can work through examples related to them, but you can check with friends, study buddies, whatever, because there's no reason why you shouldn't be able to get pretty much 100% on all of these homework questions, right? Theoretically, or at least close to it. Like obviously there's I'm quite confident of this answer even though I am wrongness type of thing, so that might still catch you every now and again, but one would hope that homework would be a little bit of grade padding as long as you take the time to make sure that you understand the concepts. Okay? But it'll be on D2L. Should go live tomorrow morning. If you have the app that we discussed last time, it will likely give you a ping to let you know that an assignment has gone live. I did activate a discussion thread so that someone, and I mentioned the Pulse app, but I could not give full directions to it. If someone else would like to give directions to how to find it on the App Store or the Google Play Store, in that discussion thread, feel free. If you have other links that you would really love to show or to give, in fact, let me see if I can. Does the audio work on this? Mm-hmm. Yeah, because I mean they do like, Adam song? Nope, that's dumb. All right, I'll find it later and link it. I just had it on my phone like a day ago because I've listened to it, and it's a really neat little chemistry, really nerdy chemistry song. Yeah.
I do actually have a question about some stuff we learned on Tuesday.
Okay, fire away.
So I was working through some of the practice problems, and I noticed that when I got to my answer with significant figures, unless it's an exact number or an exact figure, should we always be answering in significant figures like that? Does that make sense?
Yes, it's a good question. What I will tell you is, with respect to the homework, and I think I'm probably going to try and do this on the test too, if I'm going to require you to answer in significant figures, I will tell you so.
Okay.
So, with accounting for or with significant figures type of thing. Some of the questions are it's going to be obvious. For example, I can give you a preview because it should be obvious. One of the questions on the homework is going to be round this number off to 3 significant figures, right? So obviously there I'm asking for significant figures. If I want significant figures, I'm going to ask for it. Now, I will tell you that, especially on those like fill in your answer type of answers, especially once we get a little bit deeper into the semester, I'm probably going to ask for it, simply because it's easier for me to tell the computer to look for a number at 3 significant figures, or a number that accounts for significant figures than it is for me to input like all 10 possible decimal places that you might have typed in. Because from a computer's perspective, 3.14 is a different answer than 3.1415.
Yeah.
Right?
Right.
So, but I'm not going to try and screw you up by not mentioning it one way or the other.
Okay. It was more so like working through the conversions. There was a couple that I just couldn't figure out where you got your answer, and then I realized it was because you...
Rounding significant
Yes,
figures.
yes.
Right.
Okay.
And that's going to be especially true in the conversions. Remember, if you ever convert between metric and American, significant figures matter.
That just should always be...
With the one exception of what? What's the one conversion that doesn't, where it's exact?
Equalities.
Well, they're all equalities. What's the one conversion between American and SI or metric that is still exact on both cases and therefore does not affect significant figures?
Inches to 2.24.
Inches to centimeters, yes. 1 inch equals 2.54 centimeters. That is exact. All of the other ones, the significant figures, which are always from the American measurement, like 2.20 pounds, so 3 significant figures for anything with pounds, that type of thing. Yes, we can argue that rabbit hole. We're going to all agree that it's exact for now. As long as we all agree on what is and is not exact, we can all do math the same way. And that's the way math works. Does that answer your question? Okay. Like I said, I'm not going to try and trip you if the point of the question is to understand significant figures, then it will be obvious. Okay? All right. Anything else? Okay. Let's talk about chapter 3, shall we? So, 3.1, classification of matter. Learning goal here. Examples of matter as pure substances or mixtures. So here we have a copper penny and we're cheating. But let's just say that copper pennies are pure copper for purposes of this illustration. So here we have a 3-dimensional spatial model of what that copper might look like, with a whole bunch of copper atoms lined up into a matrix or crystalline structure. This is an element that happens to also be a pure element, a pure substance, because it is made out of entirely copper. Once again, by way of our oversimplified example. There's another minor rant about coppers. Oh, I never gave you the rant about degrees of wrongness, did I? There's a minor rant about pennies. I hate pennies. Pennies are worth, it costs more to make a penny than the value of a penny. In the US fiscal system, we should get rid of pennies and probably nickels while we're at it and just throw it all out and just round everything to the dime. Because, when you could buy something significant with a penny, then sure. But you can buy nothing significant with a penny. So, how many of you reach down and grab pennies when you see them on the street? Be honest. We got one hand over here. 2, 3, 3. maybe 4-ish. Does it matter if it's heads or tails? Is it just the whole luck thing?
No, it's because you can buy people's thoughts.
Because you can what?
A penny for your thoughts.
Oh, penny for your thoughts.
That's an economy that never changes.
I see. Most thoughts are also free, or if I needed to require you to pay me for them, I would charge you much more than a penny. But most of my pennies I end up leaving in like the somebody else needs a penny later jar type of thing at gas stations or whatever. So yeah, pure substances, elements. Elements are composed, or a pure substance is composed of one element. We can classify matter, which is what we're talking about here, as anything that has mass and occupies space. Pretty much anything that you are going to be directly interacting with is matter. Now, do you directly interact with something other than matter? Is that sort of a trick question? You also directly interact with energy. Specifically, there is a type of energy that you are directly at least absorbing, if not interacting with. No, that's not fair. You're giving some of it off too. You're converting it from one form to another. What am I talking about? Electromagnetic energy, otherwise known as light. We'll get to that later. I don't think today, though. So, anyway, here we go. Light being this interesting thing that sort of has, that doesn't have mass, and yet also is affected by gravity, which affects mass, whatever. So, water, wood, plastic bags, the table in front of you, the pencil, the computer, the paper, the air that you are breathing has mass, is made of matter just as much as the table and the ground beneath you and the clothing that you are wearing and the body that you are made of. Your body is composed of elements. We can classify all of that matter based on its composition. We've got pure substances here. These things have fixed or definite compositions, so that particular substance doesn't change. We have mixtures that are combinations of more than one pure substance. So here we have a lovely flow chart. So we start with matter up at the top. We've got pure substances that can either be elements or compounds. What's the difference between an element and a compound? Because we haven't been told quite specifically in a slide yet, so you don't have anything to quote. Unless, of course, you actually already know this.
An element is homogeneous, a compound is made up of one or more elements.
There you go. An element, you could say homogeneous or is a monomixture. It is not a mixture, it's the same thing. An element is one thing that is, you can put a tiny little asterisk next to this, all exactly the same. Because we're going to talk about later about how different aspects of elements are not actually all exactly the same. But for now, until we get there, we can consider them to be all exactly the same. So, copper penny made entirely out of copper. One element, a pure mixture, right? Compounds like water, and the vast majority of everything else you interact with are compounds. They are made up of more than one type of element. So what are the two elements that compose up water? Hydrogen and oxygen, right. Pretty simple stuff. Then we get, instead of pure substances, we get mixtures. So what's the difference between this homogeneous mixture of brass and this, otherwise you could say also homogeneous mixture of water? Because, I mean, water is always going to come as H2O, right? I'm sort of lying to you. Once again, this gets sounded like, well, how much are we oversimplifying here? One could argue, well, technically water will sometimes automatically subdivide into a hydrogen and hydroxyl ion of equal proportions, depending upon the pH. So you just have to, we can get deeper into that if you wanted to. We don't need to right now. But generally, this is a homogeneous mixture, but we call this a compound. What's the difference between this homogeneous mixture that we call a mixture instead? Well, the brass and the copper, even though we've drawn these in this beautiful little matrix that we have here, brass and copper do not actually form this necessarily equal, copper and zinc do not form this equal ratio and perfect matrix. But it is a homogeneous in as much as that when you look at this tuba, sure, let's call it a tuba. I don't have a person for reference of size here. Let's call this a tuba. When you look at that, there aren't going to be spots of it. I'm having a minor earthquake here. There aren't going to be spots where it's like, that's obviously where the zinc came in, and then this other bit over here is obviously where the copper comes in. It's all just brass. It's all this even mixture of copper and zinc. But what's the difference between that and some other compounds that we're going to talk about later? Well, for one thing, this mixture of copper and zinc, even though it is homogeneous or has come to an equilibrium with its concentrations, it can be separated from each other via mechanical means if we're really, really careful, but really what we're talking about here is that those things are just hanging out because it's the only way to be. We're going to talk about a compound later called sodium chloride. You know, guys know what that is? Salt, right? Sodium chloride is a compound, not a mixture. Why? Because even though sodium and chloride are not covalently bound in the same way that the hydrogen and oxygen are here, if you don't understand what covalently bound is, don't worry, we'll get to it later. Even though hydrogen and oxygen here are holding hands in a semi-permanent manner, sodium and chloride are also reacting to each other. They are associating with each other. The term that I like to use as a metaphor is they are sort of holding hands in a manner that enforces a very specific and universal ratio of sodium to chloride. But when we made this brass tuba, we did not guarantee that there was a 1-to-1 ratio of copper and zinc. We do not guarantee, because of the inherent nature of the atoms, that they will align in this beautifully drawn crystalline matrix. But they will pretty much mix evenly and create a thing we call brass, which we then pound into something we call a tuba. So this is a mixture. And then we have a heterogeneous mixture, which is very poorly illustrated like water and copper. Could you give me a better idea of what a heterogeneous mixture might be that we've actually already discussed?
Alcohol and water.
Alcohol and water, or perhaps an olive oil vinaigrette dressing, right?
Is that ever homogeneous?
Yeah, it's heterogeneous. It is not a homogeneous mixture. By definition, a vinaigrette is not homogeneous because they will desire to separate from each other. Even if you manually mix them, it will never reach homogeneousness. It could reach something close to it for a millisecond or two if you're really forceful.
Is there elements of it?
It's going to be heterogeneous in that case. So a heterogeneous mixture is multiple compounds put together where they will never achieve any sort of even distribution. If they achieve an even distribution, then what would we call it? Homogeneous. Which, copper pennies inside a glass of water, that's never going to happen, right? So, let's talk about pure substances. So we're going to go back a little bit, or define an element, a type of matter with a fixed or definite composition. An element is what we use to define that smallest aspect of the composition of that pure substance. So a pure substance is composed of one atom. If it is composed of only one atom, then that is the element that we are describing. You can't have a pure substance composed of a compound, which is two or more elements, therefore two or more types of atoms. So when we're talking about very simplistic chemistry, you can use the word element and atom not quite, but almost interchangeably. An element describes something that we can collect as atoms. A compound is composed of two or more elements, which means it's composed of two or more different atoms, different types of atoms. The reason why they are not exactly different is because you can have a soda can made out of quote-unquote pure aluminum. How many atoms are involved in the composition of that soda can? A bunch. Way more than one. But all of those atoms are, once again with that tiny little star next to it, all the same thing. They're all just aluminum, which means they all have similar chemical, if not exactly the same chemical properties. That is, in fact, what makes an element, is that it has all atoms of the same element have the same chemical properties. If you're not sure what I mean by chemical properties, don't worry. We'll define what those are. You can have a pure substance made up of copper, which we abbreviate Cu. You could have it made up of lead, which we abbreviate Pb. Made up of aluminum, which we abbreviate Al. What do you notice about all three of those abbreviations? What's the first letter? Always uppercase, and the second letter is always lowercase. Not all elemental abbreviations have two letters. Without looking at the periodic table over there, name one that does not. It has just one letter. Oxygen, nitrogen. Anything else?
Carbon,
Carbon.
Things that end in N.
hydrogen.
Interesting. Hydrogen, yes. So, we're going to talk about the periodic table of elements extensively, but not quite yet. So compounds are those that consist of more than one element. H2O2 is hydrogen peroxide. Table salt, sodium chloride. Why is it that our abbreviations always have capital or lowercase letters? If you were to see something like H and O next to each other, would you assume that that is the element homerium? If it was a capital H and a capital O? No. Why? Because they're both capitals, right? So you would know that that was hydrogen and oxygen, that we were describing a molecule that somehow contained only one hydrogen and only one oxygen. It is not impossible. In fact, those particular molecules are quite common, especially in aqueous solutions. We call that the hydroxyl ion. Usually we would represent it as HO minus, but we'll get to that much later. NaCl, you know that that's two different atoms. How? Because the capital N and the lowercase a tells you that's one element, right? And the capital C, lowercase l, tells you it's the next. We're getting a little bit beyond the slides, but I'm wanting to make sure that we're all on the same page when it comes to chemistry, right? We have to speak the same language if we're going to understand each other as we move along. Sugar, C12H22O11. That's cheating. This is describing table sugar, which is actually sucrose and glucose, or excuse me, which is sucrose, which is glucose and fructose, covalently bound via an ester bond. Let me follow that. You will, hopefully that will be easy. If it isn't already easy, by the end of the semester that should be easy. And then of course we have water, H2O. Have you guys ever signed those petitions about oxygen dihydride and how dangerous it is and how we should regulate it and ban it?
Hydrogen monoxide.
Or, yeah, hydrogen monoxide, yeah, oxygen dihydride. Yeah, so, you know, how it's deadly in high concentrations and has killed people and interesting things like that. It's just an illustration of how science ignorance is a punchline. Because that's water. And yeah, water can kill you, but you also have to have it, right? How long can you go without a drink of water before you start suffering severe effects up to and including death?
3 days.
3 days. How long can you go without food?
3 months.
Yeah, a week or two, depending on where you're starting from, sort of. But yeah, 3 days of no water, you're in pretty bad shape.
Surprised we disagree.
I'm gonna set that on a shelf.
I'm on 24 days.
So, there's a guy over in India, was it India? That swears that he lives on nothing except the energy from the atmosphere and the water from the morning dew. I don't believe him either. There's also a guy who swears he's never pooped in his life. I don't believe him. There's a guy who says he's never showered. That I can buy. Anyway, what's the difference between H2O2 and H2O? Well, one has an extra number, right? H2O is water. H2O2, what's it got an extra of? It has an extra oxygen atom. But that shouldn't make a big difference, right? I mean, you should be able to use these things relatively interchangeably, right? Because everyone knows it's perfectly safe to drink hydrogen peroxide, right? Don't ever drink hydrogen peroxide. That's one of those, like, you gotta be careful. That extra oxygen atom that's in hydrogen peroxide makes a really big difference. But it is that extra oxygen atom, and therefore the change in shape that is required in order to make that stable molecule, that gives that chemical its properties. There is absolutely nothing that separates this water molecule from that sugar molecule. They are both made out of the same physical things, i.e. atoms. And yet the order and chemical properties of the atoms that make them up will give them very, very different properties. In the same way that if I make a teddy bear out of lead, my children will not love it. But if I make it out of cotton, they might. Still not a guarantee. Compounds contain more than one element. Table salt is made out of sodium chloride, but we can separate that sodium chloride compound into sodium metals and chlorine gas. That sodium metal is a really fun thing to throw into water later. It's rather explosive. Exothermic reaction. So this process is deceptively simple on this slide. Salt is not that easy to separate into sodium metals and chlorine gas, but on a daily basis you do chemically separate table salt by doing what?
In water.
By dissolving it in water. Whether you realize it or not, when you're adding your salt to your food, what happens either the moment it touches your food, or if not, if it's really dry food, the moment your food touches your tongue, that salt will dissolve in water and break down into sodium and chlorine, except both in aqueous form. So there won't be any tiny explosions on your tongue. Thank you. Mixtures can be separated. Here we are straining a mixture of water and pasta. Metaphorically applicable. Chemically not so much, but you know, it's hard to describe chemical separation or physical separation other than this. So here we have a mixture, or what was once a mixture, pasta and water. We can separate that mechanically by running that through a strainer. The water goes through. The pasta, one would hope, does not. We can do the same thing very similarly with chemicals. We can separate them in any number of means. Here we are separating with a filter. This is pretty much exactly the same thing as the pasta and water, with the exception of a much smaller pore size on our colander. And then here we have a separation of different chemicals based on how they move up this paper in liquid chromatography, which is really neat. The way things move in a dissolved solution in relation to how much they don't want to move as they are interacting with the binding paper that is moving up. So if you're something that doesn't care about sticking to this paper, you will climb this paper at the same rate that the water or alcohol solution down here is climbing the paper, because you're just dissolved in the liquid, moving right along with it. But if there are any chemical properties that make you want to grab onto this paper, it's like the difference between trying to take a child to the bathroom for a bath at night when they want to take a bath. They're very eager to go with you. But if they don't, they will reach out and grab every possible thing they can to slow you down. Well, the children that like baths are moving with the solvent. The children that don't like baths are holding on to the paper. And if we take this metaphor and apply it to chemistry, what is it about those chemicals that make them not like baths? It has to have something to do with differences in their chemical makeup. A water molecule does not just decide that it doesn't like oil molecules one day. It always doesn't like oil molecules. And so if there is a difference in how those ingredients react to that paper, it is because of a difference in which elements are combined in which way to make up that compound. Because those physical differences have to come from a difference in how that compound is made. Even if it's made from exactly the same atoms, if we organize them in a different way, we can have a compound with a different physical property. Homogeneous mixtures, relatively, if not in fact by definition, uniform throughout the sample. We cannot tell which parts are where. If we could, it would not be uniform. Once again, brass is not an even commixture between copper and zinc, but it looks like it in the picture. I'm only telling you this because I actually know a little bit of metallurgy and care. Most people wouldn't care, and so it's just like, look, it's the thing. So, you know, color these balls differently, and you've got exactly the same picture. They give us some sodium chloride because it just makes for a nice graphic. This is where the art department in science textbooks really needs to get a better science education. But it works. How about something else as a homogeneous breathing mixture? So the scuba mixtures that you might use when you go scuba diving, nitrox, a homogeneous mixture between oxygen and nitrogen, heliox, oxygen and helium, which that would have to leave you, A, give you a headache, and B, leave you talking really weird when you come back up. I don't know, I don't scuba dive. This is another one of those hobbies that I would love to pick up, but I need another hobby like I need another hole in my head, and it's not an inexpensive hobby, so it's never going to happen. Unless, of course, I decide to take another cruise, and then I might figure it out so I could go scuba diving on a coral reef before they all die. Trimex, oxygen, helium, and nitrogen. Why would you want something that's oxygen and nitrogen? If you're scuba diving, why wouldn't you want just pure oxygen? There's a myriad of reasons. One, pure oxygen is really dangerous. Transport and storage. What's the primary component of the atmosphere that you're breathing right now? Nitrogen. Upwards of 70% nitrogen. So why not, if you're going to make a pure gas that you're shoving into a tank so that you can breathe it underwater, why not make something that's kind of like what you're breathing now? A heterogeneous mixture is the example given with the pennies in water. Varies from one part of the mixture to another. And the different parts of the mixture are visible in some way, shape, or form. Once again, perhaps a better example of a heterogeneous mixture would be a vinaigrette dressing, right? The oil and the water. They do not like to mix. You can force them to, but you can still see the divisions. Even with a really vigorous shake, you can see the little oil droplets in the water. Heterogeneous. All right. Let's talk about properties of matter. Silica are the gray ones, oxygen are the little red ones, and here's a nice little space film model to give you an example. And I honestly don't know if that's the accurate example, but it might be. But once again, I don't know how much I trust the art department, of what it takes to make an amethyst crystal. We can take these same two atoms and organize them in a myriad of different ways to make a myriad of different, sometimes we call them elements, but that's because amateur geologists and rock collectors are inappropriately using scientific terms. What's a more appropriate term to describe this? Perhaps a mineral? Did you have another one? No? If you go to natural history museums, they'll give you all sorts of these different calcites, fluorites, things like that, the description for these minerals. And the differences that you see in the crystalline structures have everything to do with the way in which those atoms organize themselves to form a crystal. Different crystals in different shapes have very different properties, even if they're made out of the exact same thing. Is there a difference between the lead? How many of you guys are actually using a pencil right now? Okay, a handful of you. Is there a difference between the lead in your pencil and the lead in the diamond ring or earring that you may or may not be wearing or may not own?
Yes.
Sure, sort of. They're both made of carbon. So, in that respect, no, they're exactly the same. But that does not mean that you should attempt to trade your pencils for diamonds. No one will allow you to. The shape of the matrix is very, very different, but they're both made of carbon. Solids. Physical state of matter. It can come as a solid. It has a defined shape with a definite volume. Solids are held together by very strong attractive forces between the atoms that make them up. Now, there are some attractive forces that are stronger than others. By way of example, the stuff that holds this amethyst crystal together is much stronger than the stuff that holds together a chunk of salt. Take this amethyst and drop it in water. What's it going to do? Get wet. Take a brick of salt and drop it in water. What's it going to do? Disappear. Dissolve. We'll talk about why later. Particles are arranged in a rigid pattern and therefore can only vibrate slowly in fixed positions. True or false, all atoms are vibrating at all times.
Except for absolute zero.
Right. We were unaware of any that actually existed absolute zero. Finding them, but it is a theoretical state. So yes, all atoms are vibrating in some manner. If they are in a solid, they are locked into a crystalline structure of some sort, and therefore their vibration is limited. Now, by definition, that means that there should be another description of matter where these particles are not locked into a rigid pattern and therefore can vibrate in any number of directions. What would we call that physical state of matter? A liquid. Liquids have a definite volume, just like solids do, but they do not have a definite shape. Why is that? Because their atoms are held together via more intermediate bonds, if there are any bonds at all, and therefore their atoms can shift around and over and on top of and under each other to occupy whatever shape it is that the container holding them currently partakes. Which is why water in a glass will occupy whatever shape the glass is, even if it's really one of those really, really weird decorative glasses. On the subject of glass, okay, I'm going to have to cheat a little bit here to give perspective, but if you go back, if you find a house that was built in the 1800s, and you look at the glass that is in the windows of that house, assuming that they have not been changed to more modern mixtures, but would you call the glass in those windows solids or liquids?
Liquid. Amorphous.
They're liquid. And yet they've been in a house since the 1800s, occupying the same shape, right? Well, that's where it's actually kind of lying. They're not occupying the same shape. If you go back and look at glass that was made a century or two ago, and you look at its shape, it will have slowly, well, let's put it this way. Imagine that you could somehow take water and make it occupy the shape of a window pane, right? With perhaps two other sheets of glass. If you immediately removed that, what would that water do? It would immediately start following in terms of flowing down because of the pull of gravity, right? Well, the glass in those windows has been doing that. It's just been doing that very slowly. So much so that you might not notice. But you could pull out a little ruler, a little caliper, and measure the top of the glass and the bottom of the glass, and guess what? The bottom would be thicker. It's a liquid. We use it as a solid. We treat it like a solid. Because it is so viscous, because it moves so slowly. Rubber's the same way. My kid has some silly putty, my daughter. She can pull it out and make it take whatever shape she likes, which should tell you something, right? Solids occupy a definite shape. She can take that silly putty out and make it take whatever shape she wants, but you put it back in that little egg that it comes in, you let it sit there for an hour, and it doesn't matter what shape it was before, after an hour of being a little egg, it's always going to be a little at the bottom of the egg, occupying the shape of whatever side of the egg it was in. It's liquid. Gases. Indefinite shape, indefinite volume. They're also going to take the shape and volume of the container where they're found. Sort of. I don't like using balloons as examples of containers for gas. Why not? What's the shape of a balloon? What's the volume of that balloon? You could define that, right? Okay, great. Now take the exact same balloon, teleport to the top of, say, the top of the tallest building in Denver. Is that balloon going to have exactly the same shape?
No.
No. Now teleport, you may not notice the difference though. Now teleport up about 5, maybe 30,000 feet. That balloon have the same shape? No. Why not?
Just broken.
Well, one, because you can't teleport. Two, let's not break the metaphor here. It might be popped, yes, at 30,000 feet especially. But what's going to happen to change that balloon? The shape is going to change. Why? Because the shape of that balloon is actually dependent upon more than just the gas that's inside it. It's also dependent upon the gas that's outside it. as you go, these balloons rise up into the air. I guess when you were a kid, you ever done that? When I was like 4, for my 4th grade birthday party, we made a little birthday card for me. We tied like 30 balloons to it and I let it go. 3 weeks later, I got a card back in the mail from whoever it was that found my birthday card, like miles and miles and miles away. It flew up into the air, kept rising higher and higher and higher until the balloon swelled up and popped, and then that birthday card fell to the ground. And someone happened to fall somewhere where someone could find it. And so they wished me a happy belated birthday 2 or 3 weeks after it happened. A total stranger that I'd never ever met in my life. Kind of neat. Gases are kind of special. The particles are very far apart and they move at very high speeds. They have very little attraction to each other. So, here's a table with convenient things about the comparisons between solids, liquids, and gases with respect to their volume, arrangement, interaction, movement, and some examples. Once again, so that you know if you need to look up some properties of matter, you can come back to table 3.1 on slide 18 instead of looking up the last 13 slides, right? If you need a refresher. All right, so those were physical states. What about physical properties? These are things that can be observed or measured without changing the identity of a substance. Because sometimes observing something changes it. So, the shape, the state, boiling and freezing points, the density. Have we talked about density before? Right. The color. These are things that are examples of physical properties. What are those physical properties going to be determined by? What gives a thing its physical properties? Which elements, in what order, make it up? What's the difference between water and hydrogen peroxide? There's some big differences, right? All because of that extra atom of oxygen, which gives it a very different shape, which gives it very different properties. Both are liquids, though, in that particular example. Copper, an element that we've discussed somewhat so far. Reddish-orange color, kind of shiny, especially if you buff it a bit. Excellent conductor of heat and electricity. And you guys have any cooking pans that have copper in them? Especially like the bottom bit, because they're really, really good at conducting heat. There's an interesting thing you can do. I would advise you do this. This is only if you A, have access to copper pipes, or even better, a solid copper tube, which most of you probably don't, because copper is actually one of those, like, if you had one, why haven't you sold it to somebody? That's worth a little bit of money now. But if you had a solid copper tube that you could wrap a dollar bill around, you could take that dollar bill and hold it over a candle, and it would not burn. It would char a bit, but that's actually the charring from the candle burning, not from the dollar burning. Because the copper is so good at wicking away that heat, at sucking the heat, that extra energy from that dollar bill that's being imparted by the burning candle, that the dollar bill will never char. It will not burn, not never. That for a short period of time, that dollar bill will not burn, even though you're exposing it directly to flame. That's how good copper is at wicking away heat, at absorbing and moving heat. Why wouldn't it work so well if it was a hollow copper tube? A lot less copper, there you go. It's solid at 25 degrees, in other words, room temperature. The melting point is 1083 degrees Celsius. The boiling point is 2500. Neither of those two temperatures would you be comfortable at. It'll melt at over 1000 degrees Celsius. It will boil, turn into a gas, just over 2500. A physical change is when we move a thing, an element, a compound, from one physical state to another, but we do not change its chemical makeup. Its composition does not change. So the example given here, water exists in 3 different states. It could be a solid as ice, it could be water, or it could be steam. Now this is an oversimplification. And I'm going to tell you this because if you look it up, it's going to be really, really cool. Look up super liquids or hyperliquids. I don't remember if I'm using exactly the right term. The point is that there are more than 3 physical states that water can exist. Each one of those states has a very specific set of properties related to the fact that it is water in that state. But there are more than 3. But I'll give you, the reason why you probably haven't heard of these other things when you look them up is because, well, they're really hard to get to. You have to have specialized equipment to force them into the right temperature and pressure range. But the 3 ways that you can find water easily on an everyday, any day of your life is either as ice, liquid water, or gaseous steam. 3 different physical states. We can change the appearance of a substance without changing its physical state. We can take this gold ingot down here, 100 grams. I don't even want to know what that's like. We could do, there's a homework problem for you. 100 grams converted to ounces, what's the value of an ounce, the current exchange rate for an ounce of gold, and it would be a lot. Gold is heavy. So that 100 grams of gold, that's quite a bit of money. But we could take that 100 grams of, what state is that gold in right now? Solid. It's not a gas and a liquid, right? We could pound it down into that sheet of gold, the gold foil. What state is that gold foil in? Still solid. Have we made a physical change to it? Yes, but we have not changed its state. We have not changed it from a solid to a liquid, or from solid to a gas, which is possible, by the way. I don't know how easy it would be to do for gold, but it is possible.
$4,200.
$4,200. That right there, $4 grand.
Yeah, it's $42.09 as of today, an ounce,
An ounce. What?
or gram.
Or a gram? Yeah,
An
so
ounce
that'd be
is
a gram.
1,300.
Right, there we go.
I'm buying.
Yeah.
Yeah. That's just nuts. Anyway. All right, so we've talked about physical properties, right? What's in between a physical property and a chemical property? A physical property describes a property related to the state of an element or compound. A chemical property is a property related to the way in which that substance in its current state interacts with the world around it. How it interacts with other substances and what it takes to change it into a new substance. When we have a chemical change, we have converted one or more substances into something new. So we can take a gaseous hydrogen, we can take gaseous oxygen, and with the addition of energy, hopefully in a controlled manner, we can encourage them to go through a chemical change to change into gaseous water. A huge amount of that central fuel tank, when you guys have watched the space shuttle go into space, right? Like, the next generation is going to say like, oh yeah, I saw that in a movie once or something, because we're not doing that anymore. But that big, huge central tank, most of the fuel in that big, huge central tank was just hydrogen and oxygen. When it burned, it produced water. Zero emission. Now, the two boosters on the side, that's a completely different story. Lots of carbon footprint in there. But that's big central one. A chemical change is when we are in some way altering the chemical properties of a substance. And the only way to do that is to alter the number, type, and arrangement of the atoms found within it. Because it is the number, type, and arrangement of the atoms in a compound that define its physical and chemical properties. So if we are making a chemical change, if we are changing the chemical properties, then we are changing the number, which atoms or which order they are in of the thing that we are talking about. This is one of the reasons why I was so happy to pick up a chemistry course as opposed to a biology course, because biology, which is where I started from, even though my PhD is in chemistry, biology at its heart is simply, in my opinion, the ultimate expression of both chemistry and physics. Because everything you are doing, even right now in this moment, is chemistry. The act of listening to me talk, the act of hopefully remembering what I say or in some way learning something meaningful from it and storing that information in your brain, all of that is chemistry. Because it is the only way that we know how to be. It is the only way that we know how to interact with the world around us is through chemistry. And somehow, through mechanisms we have yet to quite figure out, it is also the way in which you remember who you are, remember who you were, and hope for who you may become. All of that is just chemistry. Forgive me if the word just seems to oversimplify that. I do not mean to. It's an amazing thing, but it's still chemistry. During a chemical change, a new substance has formed that has new composition, new physical properties, new chemical properties. If we take iron nails, put them in a little bit of water, especially salt water, and leave them out, what's going to happen? They're going to rust. Is somebody dancing on the floor above us or something? We're just having a minor. Oh yeah, I bet that's true. So, when that happens, it's not just pure iron in those nails anymore. The iron on the surface of that nail is reacting with oxygen in the water and the air, and it is forming a new compound, iron oxide, otherwise known as rust. By the way, here's a biology joke for you. Do you know why our blood is rusty? Darn it, I ruined it. Do you know why our blood is red? Because it's rusty. What does our blood do? It carries around oxygen, right? What's the central atom that does that? We have a term that we like to use to describe the amount of dissolved oxygen in our blood. That's fine. That's just dissolved oxygen. That's not, well, it's a little bit different, but it's not that much different than the amount of oxygen that's in the lake outside or in the water that's coming out of your tap. So why is it that your blood can carry around so much more oxygen than just pure water? Because you have something in all of your red blood cells whose sole job it is to carry a buttload more oxygen than that. And the thing at the center of each one of those hemoglobin molecules that does the work of that molecule is iron. And what does iron look like when it has oxygen attached to it? We call it rust. It's red. Why is your blood red? Because it's rusty. Interesting sci-fi fact. Any Trekkies in here? Vulcan blood is green. Because according to Gene Roddenberry, guess what's at the center of the oxygen-carrying molecule in Vulcan blood cells? It's not iron, it's the Statue of Liberty. Copper.
Chlorine.
Hmm?
Better than chlorine.
Better than chlorine. Why does carbon monoxide kill you? Because carbon monoxide will covalently and permanently attach to the iron at the center of the hemoglobin molecules in your red blood cells. You suffocate when there is plenty of oxygen in the room, because the carbon monoxide will selectively kill, if you will, the function of the thing in your blood that lets it carry more oxygen than just regular pure water. Even if there's plenty of oxygen in the air that you are breathing, you will suffocate from lack of oxygen. Iron. That is a reversible chemical reaction. Collects oxygen from your lungs, lets go of it, and gives it to the rest of your body. But that also is just chemistry. Physical and chemical changes. We've described them all. Physical change. Water boils to form water vapor. But that's a physical change. Why? What were we when we started? Water. What were we when we're done? Water. But we changed state. That's a physical change. We're still just water, right? But if we take water and add, say, take water and let it fall from the sky through some air that has a whole bunch of sulfur in it because it's up kind of downwind, if you will, from a coal plant, and it picks up that sulfur and it lands as sulfuric acid on the ground. Is that a physical change or a chemical change? Chemical change, because we have taken multiple compounds, combined them into something new with new properties, even though both of them are liquids. So, example of physical changes, example of chemical changes. Did you have a question? No? Okay. Summary of physical changes. Characteristic of a substance or physical property is it just what the color, what the shape, the odor, size, melting point, density, etc. If we have a physical change, we are changing a physical property that retains the identity. Still water, it's just changing from gaseous to liquid. It's still gold. It's just changing from one solid to another solid, i.e. gold bar to gold leaf. Chemical changes, something that converts from one chemical to another, one substance to another. And the new substances have different chemical properties than the substances that they were to begin with. All right, so we've gotten through 2 things. We've been here for about an hour. Oh, shoot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We're all here. Good. All right. Let's go ahead and take a 10-minute break. We'll pick it up with temperature here. Stretch your legs, do some jumping jacks, get a drink. Some Doritos or something. Everybody wake up. Super important. You just remember chapter 2, whatever the syllabus. The only thing I'll say is that since you weren't here,
Yeah.
Homework is going to be online,
Yeah.
which, I mean, this is all in the syllabus, but homework's going to be online.
Where is the syllabus? Because I looked on D12 and I couldn't find it.
There's that introductory page in D2L that says, hey, welcome to class. There's a thing that says, click here.
Oh, okay.
And that's the link to the syllabus.
Okay.
So click there, and there's the syllabus. And so homework's going to be online. It should be posted probably after class every Thursday. It'll be due by the next Thursday's class.
Okay.
It's going to probably be all online. I might have to give you a worksheet once or twice.
Okay.
I don't know, we'll see. And the exams are all going to be online every other week.
Okay.
They will also go live
Are
after
they on
class on Thursday.
Thursdays?
Not on Thursdays, no. They're going to be online, just like your homework, just bigger.
Okay.
They'll go online. They'll be live Thursday after class, or excuse me, Friday morning, and you will have until Sunday at midnight, so 11:59 p.m. Sunday night, to start it. Once you've started it, you'll have a 2-hour window to finish it.
Oh, so it's not in class?
Correct.
Oh.
I'm not sacrificing an hour every other week to take a.
I'm not gonna fight you.
Okay.
I'm not
Right,
complaining.
yeah, it's gonna be
I
online.
was just shocked.
Yeah.
Okay,
So it's
awesome.
online, so therefore it's open book, open note, open friend. But it is going to be a timed test, and it's random block, which means that even if you do have a friend,
You're only gonna say questions.
right. So you can still sit there and help each other take a test, and that's fine, because then you have to explain why you think the right answer is A, B, C, or D. And if that explanation helps you to finally understand and figure out and maybe even remember that concept, then my job is not to test you, my job is to teach you. So that's why I do it that way.
Okay, awesome.
So, but yes, and then if you forget or miss, the exam will stay open after Sunday, but you lose 10% for whatever grade you get for every day that you were late. So it's not the end of the world if you forget, like, go to bed because you're tired Sunday night and you totally meant to take your test, but then you can take it sometime on Monday and just lose 10%.
Awesome, thank you.
Yes.
That's the whole
Um,
piece.
there will be a discussion post as soon as I get it up with as much of the video as I was able to capture on Tuesday.
Okay, thank
My
you.
battery kept dying.
Okay.
So you're recording this?
I recorded.
With my
You
permission.
can go back, you put Adam up on the big screen.
Yeah, you can capture all of those nefarious things that I'm saying and announce them to the world.
So if
Did you
there
know
are
your file was in
classes
zip
that,
last week?
Did I what?
Did you know your file was in zip last?
See, you say that because I'm nervous about that. That's like, one of those things where I have to check every time I walk into the room. But anyway, yes.
so if we miss a class, we can post.
That's awesome.
It is his intention with my permission, because I used to record my lectures anyway. So, and I would have done that anyway here, but unfortunately all of the technology that I had at my previous institution, in order to allow me to record my lectures, was property of that institution. So when I left, I had to take me with me. So I'm fine with the lectures being recorded and being made available for students so that you can catch up, catch the parts that you miss. Unfortunately, even though we are recording our lectures, that does not change the attendance requirements from Columbia College.
So what do you mean required? That's for like if you have financial aid though, right?
Yes.
Because I've had classes in the past where we actually got attendance points, and then I've had other ones where it's just, you have to have a certain
Right,
attendance.
yeah, no, not being here is not going to hurt your grade in some manner, other than it might impact how well you pick up the information, but it's not going to inherently hurt you if you are not here. That being said, I am required to keep attendance, and so if there is any attendance-related policy about not being in class, then you may still run afoul of that. So me personally, I wouldn't care, especially since the lectures are online. Theoretically, you could never come to class. You could log in and do your homework every Friday night, and you could log in every other weekend and do your tests every Saturday afternoon, never show up in class and still get an A. Because if you know this information, then you know this information, right? And you just proved it by taking the exact same metrics and rubrics as everybody else who came to class. But the problem is that every institution has different rules about how they incentivize and require students to actually attend the class, and especially with respect to how their personal policies integrate with federal policies. So yes, the main thing is if you're getting any sort of financial aid, the federal government is not kosher with handing out money to people who don't actually go to school to do the thing they said that they were going to do to get the money in the first place.
It's okay, then we'll pay back.
So you can't miss more than 2 weeks like consecutively. So it's like once you miss your third class, your fourth class, you can be dropped.
But that's if you have financial aid though, right?
I
Like
think
for me, it's like.
I think it's Columbia College's policy if you have a C or lower in the class, and then it's like if you have financial aid, it's your policy in general.
Yeah.
Are you familiar with flipped classroom? Pedagogy is just undergoing a massive improvement, especially with our really difficult cram an entire book into 8-week sessions.
Yeah.
The flipped classroom is the teacher records the lecture along with often a screen tracker, so you can draw on the screen and stuff and add narration. And then your job out of class is to watch the lectures. When you come in here, it's all troubleshooting,
Right.
mastery. I didn't understand this part, and you spend the whole period.
Right. Small group sessions, interactions, working about your homework, doing little things, talking to the teacher about application, and doing the things that you have to already have mastery of the subject before you can even do it. And so it's definitely a intriguing and interesting way to do it. It requires a lot more work up front on the part of the instructor, and it requires a lot more investment from students as well. Because if you don't watch the lectures, you come to class and everybody is talking circles around you and you can't make any contributions, and then that means that what you get out of the course will also be very limited too.
Yeah, but once you got the up front, you can just post.
Sort of, yes, sort of.
So are you in this class, or are you like a student teacher, or
I'm
like,
a dork.
so you are in this class? Like,
He
you're
is
a
enrolled as a student in the course.
student? Oh, okay.
I am tired of computers. I wanna say, hello, I'm Christian, I'll be your nurse. And,
Okay.
do you know what the fully cat is? You can just put the fine.
That's put in so many rules and qualifications. You don't have to be there.
Depending on where you
So yeah, with respect to attendance, I'll take attendance probably around 6 o'clock, just because I don't, like I said, I don't mind if you come in late as long as you're not disrupted. But, and so theoretically, you can kind of cheat from that too. I'm not going to be a Nazi about it, but I do have to follow the policy and enforce the policies of Columbia College. So there's some wiggle room in there. But yeah, my perspective is you're all adults. You're paying for this one way or another, either out of pocket now or over the next 30 years of your life. So I will give you the room to fail and enough rope to hang yourself with if that's what you really want to do. But I would really rather that you don't do that, and the easiest way to not do that is to come to class. But I was also the type of person that when I first got to college as a bright and shiny 18-year-old freshman, I walked into my freshman biology course, which had a required attendance policy. If you miss more than 3 days, you lose a letter grade. And so in the first 2 weeks, I proceeded to miss my 3 days, and then for the remainder of the semester, I showed up and laid my head down at a desk and slept. I was technically there, but I was also quite visibly telling a teacher how much I thought of his attempt to be my mother. So, but I don't get to make all the rules. Question?
Okay, so I've noticed with these notes, they correlate heavily to this book,
That is because they are made by the
but I mean,
publishers of the book, yes. I edit them a little bit, but yeah, they're just going to follow the book pretty straight.
part of me is like,
Why
should
did
I
I get
keep
the
this
book?
book?
Here's the thing. I can totally appreciate why you might have that picture. Here's the thing. I use these slides to keep me on topic because as probably is already apparent, if I don't have something to keep me on topic, I will end up over there, right? So the slides keep me on topic, even the ones that are repetitive, I use them to make sure that I'm staying on topic, talking about the things as we work through the book. But that does not mean that the way I explain something is going to make it stick for you. So the book is effectively another person's perspective, another knowledgeable instructor's perspective, and their attempt to explain the information to you. Now yes, the organization of the slides is going to look very similar to the book because that's how the publisher is the one that put it together, right? But that does not mean they're going to use the same terms, it does not mean they're going to use exactly the same examples, and the book is going to go into a greater depth than the slides do in explaining these concepts and differences. If you do not feel that you need it, then maybe you don't need it. Because what I'm not, if I do manage to put all of your quizzes online, then you don't even need the book to be able to answer question 4, because homework isn't going to be answer questions 4, 8, 15, 17, 29 from chapter 2. Like that's, so you don't even need it just to look up the questions. And even if you did, you could like share a book with somebody else who had it and take a picture of that page or something, right? So like, so I am and have always been of the opinion that your textbook is a very good reference. It is excellent as a secondary means of getting access to the material. It would be a very good thing if you read the chapter before you came to class, and that way you already have some exposure, and then I'm just going to give you another different viewpoint on it, and so it'll reinforce that information. But just rereading the chapter over and over again is not going to make this information stick in the same way that rereading these notes or even watching the recorded lectures, none of that is going to make it stick by just doing that. It doesn't matter how many times you read this information, it is not going to stick in the same way as if you take the information, synthesize it, reorganize it, and do something with it, and then that you might actually carry with you. a lot of this is going to get flushed, because that's what happens in every class. My intention is to structure the class in a way to minimize how much of that. How much benefit you get from that book is really up to you.
Yeah, because I was just thinking about like worksheets, because I feel like mathematically, like chemical equations, that's the stuff I'm really gonna have to like soak in. And
Yeah.
I found some stuff online, but I mean,
And the book is going to give you a lot of extra problems that you could work through that on top of the problem slides, right? Book's going to have even more, different ones. You could find some topical problems by just doing a Google search, I imagine. But it may be very topical. It might also be kind of like over there, and it might just confuse you because the way they're expecting you to do it isn't the same way we've described it. It really depends.
Did you find out if you access to the online materials that?
No, because access to the online materials is more than likely, unless it's simply access to the slides, which that's a teaching resource, teacher's resource. But there is an online component to the book, but that's if I wanted to work through the publisher to make quizzes and things like that through their website. So I'm not doing that. So you shouldn't need any sort of online access through the publisher of the book for this course. Right, an access code. You shouldn't need that. That might give you access to other resources that maybe they have online, but I'm fairly certain that that is something that you would also have to pay for, or that I would have had to enroll in and design through their website, which I have not done. So even if I got one for you, it would be heavy.
And typically to buy a new book that has
The access code, yeah. So, yeah.
they can
All right, any questions about what we talked about so far? Shall we continue? Let's talk about temperature, something that I have sort of complained about already. So, temperature is a measure of hot or cold. It's a measure of the relative degree of heat, perhaps. We use a thermometer to measure it. We measure it in degrees Celsius, or over here in America, degrees Fahrenheit, because we're weird. But we are also very set in our ways, so there you go. What is temperature? This gets deeper than what this, but this book is trying to keep it simple. In my opinion, too simple. What is temperature?
Measure of how fast atoms are vibrating.
Yeah, it's a measure of, well, let's get even more complex than that. What is the vibration of an atom? What type of energy is the vibration of an atom?
Electromagnetic.
No, well, sort of. You can have electromagnetic energy, but that electromagnetic energy is going to be absorbed and then converted into a very specific type of energy that we call kinetic energy. Temperature is quite literally a measure of the amount of kinetic energy an object has. And not just kinetic energy in terms of a bullet flying through the air, but also a bullet while it's sitting on the ground. Individual atoms within that bullet are going to be vibrating with a certain degree of energy. And the more vibrations they take, the faster their vibrations are, the higher their kinetic energy will be, and therefore the higher their temperature is. What is the difference between water as a gas and water as a liquid? What do you have to do to convert water as a liquid into water as a gas?
Half a calorie.
Add a crap load of energy. Way more than half a calorie. Well, depending upon how much of it we're talking about. We're going to have that in here. So, you add a lot of energy. And somehow simply the aspect of adding that energy in the form of heat gives those molecules the ability to stop holding on to each other in the form of a liquid and start being so distant from each other that they are now a gas. And what happens to that gaseous water if we cool it down by extracting energy from it? Stops vibrating so far apart from each other and condenses down into a liquid. Temperature is a measure of the average kinetic energy of an object, even while at rest, which we perceive, thanks to our senses and our mind, as hot or cold. If it has less average kinetic energy than the surface of your skin, it will feel cold. If it has more average kinetic energy than the surface of your skin, it will feel hot. We measure that difference in kinetic energy, that difference in temperature, as degrees Celsius or degree Fahrenheit or even potentially degrees Kelvin. So, like I said, that's just a tiny short rant for me because I dislike the degree of simplification of how we describe temperature in this book, but we can pretty much stick to this moving forward. I'm not going to fault someone for calling something cold, although it might make me shiver in revulsion just a little bit. I still do it. I'll still look outside when there's snow and go, wow, it's really cold out there. It's a natural thing to do. Temperature scales, Fahrenheit, Celsius, and Kelvin. We use reference points on those scales to define what the boiling point and freezing points of different molecules are. Now, we use water once again as the way in which we define these scales. The convenient thing about the Celsius scale, you'll note, water has a freezing point at exactly 0 degrees Celsius. Water has a boiling point at exactly 100 degrees Celsius. Do you think this is just convenient that we happen to pick this scale with these numbers that happens to exactly coincide with these two physical change of states of such a common and ubiquitous material that we can find all around us at any given time? No! We have this scale because we have this common and ubiquitous material that has two changes of states at very specific points. And we pick those 2 points and then subdivided everything in between by a certain arbitrary amount to give it 100 degrees of difference, which gives us a line that we can then graph what temperature is above that 100 degrees or below it. Fahrenheit, I don't even know where Fahrenheit comes from. Like, honestly, just one of those, like, I think there's a guy named Fahrenheit who invented it. I don't remember why it's 32 degrees is the freezing point. I don't know. But that's the scale that we use. Water freezes at 32 degrees Fahrenheit. It boils at 212 degrees Fahrenheit. Kelvin, the freezing point of water is 273 degrees Kelvin. You'll note that the boiling point of water is exactly 100 degrees higher than that. Kelvin is a scale that was based off of the Celsius scale that then mathematically extrapolates, if we kept getting colder, what is the absolute coldest that we can get? In other words, how much kinetic energy can we extract from an object before it literally stops moving, period? Are you moving right now? Yes. You are moving. If I was sitting in your place, I'd be tapping a foot or wiggling it or something like I can't, you may have noticed, I can't stand still. Even if I was in a coma, my atoms would still be vibrating. I would still have a temperature because of the air around me in the room where I was being stored. So therefore I would still be moving. Even if you froze me as solid as you could get, I would still be moving because the planet is rotating, it is rotating around the sun is moving around the center of the galaxy, the galaxy, and the galaxy is moving through the universe, yes, galaxy is moving through the universe, so we're all moving, like this is why reaching absolute zero is such a really freaking hard thing to do. But mathematically we can extrapolate where that would be, and it would be at 0 Kelvin. Getting to 0 Kelvin is not quite impossible, but it's close.
So that means it's happened?
It means that there are groups that claim that they've gotten really, really close. Like close enough that maybe we could almost be like, but you can't do this with, you will find no freezer that will keep your food at 0 degrees Kelvin.
Very active in measuring it.
Yes, like attempting to define it, yes. It interacts with it in a manner that would impart, yes. So, yeah. So, anyway, those are the scales. Celsius, Kelvin, very closely related. They use the same scale. Now you'll note that there's a 180-degree difference in between the boiling and the freezing point in Fahrenheit. So 1 unit Fahrenheit is not equivalent to 1 unit Celsius, but 1 unit Celsius is equivalent to 1 unit Kelvin. Here's your exchange factor. Do you ever think that might come in handy? You know, an exchange factor. 1.8 degrees Fahrenheit to 1 degree Celsius. Where have we seen exchange factors before? Oh yeah, half of chapter 2, right? Here's the equation to convert between Fahrenheit and Celsius. This is if you want Fahrenheit and you are given Celsius, temperature in Celsius, T sub C, 1.8 times T sub C plus 32. So there is your 1.8 right there. And then we adjust our freezing point by adding 32. Because Fahrenheit doesn't freeze at 0, right? It freezes at 32. You can do a little bit of calculus and turn it into this equation right here. If you're given Fahrenheit and you want the calculus, a little bit of algebra, excuse me, to get the Celsius temperature down here. If you're unsure how to go from this equation to this one down here on the bottom, you can talk to me later and I'll show you on the board. And if you're still confused, then you should review your algebra, basic algebra a little bit. So if you're given 21 degrees Celsius, you want temperature in Fahrenheit, how do you do it? Well, in this case, you write down the equation, you plug it in. So what, if your room is 21 degrees Celsius, what's the temperature in Fahrenheit? 1.8 times 21 plus 32. 1.8 is an exact number in the equation, 32 is an exact number in the equation, but we are given a number here with 2 significant figures. So we have an answer to the ones place here of 70 degrees. Everybody follow that? Basic algebra with the inclusion of those annoying significant figures for how far out we take it, right? What's 1.8 times 21? Somebody whip that up real quick, would you please?
$37.8.
37.8. Why is it rounded to 38?
Because it's too significant.
Right, because 21 is a measured amount, right? And it has 2 significant figures, so 37.8 becomes 38.
So I watched a YouTube video on significant figures.
Okay?
And they said that you, and I'm learning that this is maybe more of a preference, but they said that you wouldn't round until
Get to the end?
Yeah.
Right.
So either it doesn't matter.
In this case, what would happen if we rounded when we got to the end? What's 37.8 plus 32?
Well, it's 69.8, so you would round up to 70 anyways.
Right.
So it works that way though.
It works conveniently in this example. It works that way that you could either do it before or after. But yes, theoretically, the best practice would be to do the entire calculations and then round to the significant figures that you have.
Okay.
Well,
Any
I was
question?
just thinking like, when you test on it, would that be better test-wise? Should we just solve the equation?
Let's put it this way, when I'm building the questions,
Yeah.
that's what I'm going to do.
Okay.
So I'm going to do the math, and then at the end, I'm going to round to whatever the significant figures are, if I'm asking for it.
If you are asking. for
Right.
it. It's like verbatim.
So you would have had 37.8 instead of 38.
Like on a homework question, yeah, I probably would have 69.8, or I would have 37.8, right. But the reason for that is because that comes out to a nice 37.8. What if it came out to 37.149683728? Like, how many numbers am I going to write down? How many numbers am I going to keep going? And that's one of the reasons why significant figures comes in, because at a calculator it's easy, because you just say, do this and add this and then add this, and the calculator remembers all of it. But if I was writing all this down and doing it by hand, how many digits are you going to write? Right? So, by understanding significant figures, you will know, well, I'll just write down a certain number of sig figs, and that way I don't need to write down 10 decimal points for everything and then round at the end. Theoretically, you should get the same number.
Right.
Theoretically.
But to follow, I mean, you're the one creating questions, so I wanna
Right.
follow your practice, so would your practice be,
I'm going to be using a calculator and then rounding at the end.
okay, and then this question, say if this question, you were wanting significant figures, would it say, the typical temperature in the room is this, what is the temperature in degrees Fahrenheit, using,
With significant figures.
okay, okay,
Yeah, I'm gonna tell you. Or it's gonna be multiple choice, and the answers will be 70, 72, 16, and 12.
okay.
Right,
I'm
and so,
still
like-
wanting that's like 69.8 or 70.
Right,
Right.
right. That, I'm not gonna do that.
Okay.
That specifically is, and if I ever do that, call me on it, and I'll give everybody the point back.
Okay.
Because that, I'm not trying to screw with you, because, like, if I wanna ask, do you understand significant figures, I will tell you. If I don't care, then I won't mention it, and it should be obvious in the answer that I'm not, that I don't care.
Okay.
But I'm not going to be trying to trick you just to make you get it wrong because you didn't use significant figures when you should have. Because theoretically, you should always use significant figures. But, does that answer your question?
Yes, yes.
I just wanted to suggest a learning resource. A lot of YouTube videos can be very hit and miss. If you want consistency, fantastic pedagogy, and
I use Khan Academy.
Khan
There we
Academy is
go.
good.
Yeah, that's fine.
Yeah.
and integration of game theory, and yeah, incentive
There's
positions.
another one by Brian Greene that I don't remember the name of, but he has a really good educational series too. But yeah, like, anybody can make a YouTube video. So,
No, no, I know.
you do have to be a little careful. But there are a lot of resources out there. And this is what I mean by multiple perspectives, like what's the value of the book. If I explain something and you're like, I don't get it, and you read the book, like, I still don't get it, and then you look at a YouTube video and it's like, oh, well that made sense because he said blah 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 blah. Like, well, I thought I said that too, but evidently I didn't. Like there's, like I said, when I was in whatever grade it is you learn fractions, I could not figure out fractions, no matter how many ways the teacher tried to explain it to me, until another kid in my class took me to the chalkboard and did something, and in 5 minutes it just clicked and never needed help with fractions again. But for a little while there, it was like, I don't understand, you're speaking German. So, like, finding someone who speaks your language. If I don't, maybe the book does. If the book doesn't, maybe I do. If neither of us do, maybe somebody online does. Kelvin. Negative 273 degrees Kelvin is absolute zero. We represent it as 0 K. There's no symbol in front of it, so it's not degrees Celsius, it's just K. Or negative 273 degrees Celsius, excuse me. Which means that there is no negative temperatures in Kelvin. There's no such thing as negative 12 Kelvin. You cannot go below 0 in Kelvin. 273 Kelvin is equal to 0 degrees Celsius. So if you need to do a conversion factor, it's just Kelvin temperature is your Celsius temperature plus 273. Easy peasy. Comparison of temperatures. The sun, let's assume we're talking about at the surface where we can actually measure it, because last time I checked we haven't been able to get, a thermometer down deep into the subsurface of the sun. So we've got almost 10,000 degrees Fahrenheit, 5,500 degrees Celsius. Hot oven, 450 versus 232. Water boils at 212 versus 100. A high fever, 104. That's like bordering on life-threatening fever, 104. 40 degrees Celsius. This is why if you know someone from Europe and you tell them how hot it is, if they haven't been here in a while, they might look at you like you're insane. Because if you said, oh, it's going to be hot tomorrow, it's going to get all up to 72, they're like, are you kidding me? Like, when they're looking outside and going, 40 degrees, wow, that's really hot. Like, you tell them it's going to be 70 and like, oh my God, it's a big egg on the sidewalk. 37 degrees Celsius. There's a lot of scientific reading if you look around at it. They'll talk about water baths at 37 degrees Celsius. Have you ever wondered why? That's why. We culture things at human body temperature because, well, when we care about things that are affecting the human body, those things have tended to evolve to grow really well at 37 degrees Celsius inside the human body. Because that's the temperature that our body actively spends a buttload of energy trying to stay at, no matter what the temperature is outside, above, or below it. Water freezes. A northern winter versus a Missouri winter. I mean, those are, I'll grant you it's a little bit, we never really got to negative 66 degrees Fahrenheit this winter. Liquid nitrogen, negative 346 degrees Fahrenheit, that's a fun one. Negative 210 degrees Celsius. Liquid nitrogen's really cold, yo. You guys ever got to play with liquid nitrogen? It's neat. You ever dunked your hand in it? Don't dunk your hand in liquid nitrogen.
Are you talking about dry ice?
No, I'm talking about liquid nitrogen. Dry ice is another fun one though, but different.
He's talking about dipping this and then dropping it so it can
Right.
shatter.
Theoretically, do not do this. Theoretically, you could, if you had a large enough container of liquid nitrogen, you could take your hand and just go bloop and pull it back out and you'd be fine. Your hand would be cold. But I don't mean like frozen solid cold, it'd just be like, whoop. And the reason for that is because as you dip your hand into the liquid nitrogen, your hand will boil the nitrogen so fast that it will form a pocket of gas around your hand, so the liquid nitrogen never touches it. And so your hand is surrounded by really cold nitrogen gas. Don't try this, because you leave your hand in that liquid nitrogen for a split second too long, and that pocket goes away, and now we're talking about the bad stuff.
Yeah, it's like when you see people doing videos where they're smelting metal and they're doing this,
Right, yeah.
their bare hand going
Yeah.
in it, it's the same.
Right, it's the same idea. So it's a neat thing, but liquid nitrogen liquefies at negative 210 degrees Celsius. Your hand is around 23 degrees Celsius. There's a 200 plus degree difference there. Your hand is a lot hotter, has a lot more kinetic energy, which means that when you stick your hand into that liquid nitrogen, it is going to lose a lot of heat very quickly and boil the liquid nitrogen very quickly into gaseous nitrogen, which is still really cold. Which is why I once again reiterate, this is hypothetically a thing you could do. I do not advise doing it. Instead, take that banana and do the same thing. Go dunk, see look, it's not solid! And then go, I'll admit to me doing something really bad. I like Mountain Dews. When I ran a molecular genetics lab for a while, I had a big dewar of liquid nitrogen. We filled it every week because we had a whole bunch of cells that we needed to keep frozen. Like, frozen. Like, negative 210 degrees Celsius frozen. I would frequently get sodas, and it's cheaper to buy them from Walmart in the 6-pack than it is to get them at the gas station, but then they're warm! So I might have put on a glove and like half dunk my soda into the liquid nitrogen just to chill it.
Every day.
For like 10 years. So, it's way too much soda, but still, it's fine.
My ex-wife liked to tell the story of a teacher who put a racquetball and then chucked it against the wall thinking it would shatter. Well, of course it did it. It went right through the wall. Because it was no longer a racquetball, it was a solid object.
Right, yeah.
You know, so.
A solid rubber ball. Frozen. Yeah, that's a rock now. That's not a blue ball, it's a rock. Anyway, body temperature is about 41 degrees C. You get hyperthermia above 41.1, you get heat stroke. Anybody ever had heat stroke before?
Borderline.
I had a borderline issue too, because I tried to be like the knight in shining armor and get out and help this girl in college push her car halfway up a hill to get to a gas station because it had died. friend of mine was just watching me the whole time, so she came out, picked me up, drove me back to her house, where I proceeded to spend the next 45 minutes lying down on her bathroom floor in the dark, just going, ugh. Yeah, that's borderline heat stroke. Here's our normal range for temperature. Above that you get fever. Above that you get hyperthermia and death. Why? Why do temperatures kill us? Allow me to rephrase. Why does cooking an egg make it change state? Yes, because the chemistry that makes up our body has certain physical properties. And if you add a lot of heat to those chemicals, you can induce either physical or chemical changes. And if they are no longer doing the job that they were doing, the job that we count on them doing in order for our bodies to survive and continue, then we die. Why does your body go into fever? Fever is a reaction most of the time. It's a good reaction on the part of your body's immune system, because here's the thing, you have evolved a mechanism where up to mild degrees of fever, your body can still function. But guess what happens to most bacteria? If not kills it, it makes it very difficult for that bacteria to grow.
This is why your doctors say don't give your children, let their fever.
Right, if it's a mild fever, let it do its job. The fever is there for a reason. Your body can do just fine. It activates heat shock proteins that will chaperone your body so that it will still function relatively normally, but certainly enough to survive, but it makes life really uncomfortable for those bacteria.
You shouldn't medicate a child's fever until it's over 102.
Unless, of course, you're trying to be a bad parent because you have to go to work and have a really mild fever and you don't want to get sent home from their daycare, in which case you medicate them just to gloss it over, completely ignoring the fact that you're being ethically inappropriate and just spreading whatever it is your kid has to all of the other kids. But then you just rationalize it because everybody else does it too, and they deserve to suffer. Yeah, exactly.
I get that all the time. They're like, oh, they weren't sick when I brought them.
Yeah.
They just developed this huge fever for
Right,
themselves.
yeah.
It's just because the Tylenol wore off.
Yeah.
Exactly.
I don't know what you're talking about.
Herd immunity's becoming
I've
a
totally
huge
never
task.
done that before. Hypothermia. What was the last one?
Hyper.
Hyper. Meaning more or above. Hypo meaning less or below. Hypothermia is when your body temperature drops below that normal range. So 28.5 degrees C. We provide oxygen-increased blood volume with saline fluids, and this was new to me, injecting warm fluids in the peritoneal cavity. It makes sense. It's like literally, let's just give you a warm fluid bath in your gut region where there's all that surface area to absorb all that heat.
Well, it's because that's your core.
Yeah, exactly. Well, that's what
Warm
needs to be
the
warmed
core.
up, but it's also the same thing. Okay, here's the thing. Where does ice melt? Think about this. You got your Wendy's ice cubes, which are honking huge. You've got your Sonic ice, which is shaved. You ever notice that? You guys eat out, and is this me? I eat out every too much?
You can buy it in bags.
Shaved ice?
Sonic ice.
Yeah.
So, Sonic ice is shaved. It's the little pellets. It does a great job of making your drink really cold really fast, but it also does a great job of watering down your drink really fast. Ice melts at the surface. Big ice cubes. They don't just go, they get smaller and smaller and smaller and smaller and smaller and smaller and smaller until they're gone. Because the surface is where there's heat exchange. The surface is where the warm things heat up the cold things, making them warmer, exposing the things just beneath them. Shaved ice melts fast. It cools off the thing around you fast. If we need to warm up your body, you have a limited amount of surface area here. What's another way to make you warmer faster? Find a way to expose a whole bunch more surface to something warm. We've got a lot of surface in here. They also happen to be, aside from this thing, the things we need to keep from freezing and failing. But yes, there's a bunch of benefits. But still, I'd never even thought of that. Like, well, that's a neat trick.
Well, when you're cold too, your blood automatically goes to
Right.
your core and your brain anyway.
Yep. The blood is sequestered away from the skin, which is one of the reasons why drinking alcohol, even though it warms you up when you're cold, is also threatens your life. Because alcohol is a vasodilator, which means that it opens up your blood vessels in your skin, so that all that nice warm blood that your body's trying to keep next to your heart and your brain slips out to your skin where it can get cooled off, and so it makes you feel warm, but it actually kills you a lot faster.
You don't realize you have hypothermia if you're drunk.
Yep. Alternatively, hyperthermia, this guy right here, that's the problem that you have if you were to, say, partake in something called ecstasy and then go to a rave or other party where you might be gesticulating in a manner that it uses a lot of physical energy. Because one of the things that E does is it cuts off your ability to sweat,
You know, and you overeat.
and you don't notice.
Well, the thing is too, is people drink whenever they take.
Yes.
And so then, all they're doing is dehydrating themselves even more, which makes them they end up having a heart attack.
Right.
Because you dehydrate yourself from
And
the
you get too
alcohol
hot.
and the X, and then you get too hot. And
Yep.
But alcohol can be miscible with water. The proper ratios will actually lower your freezing point, so you can get a lot colder.
No.
No.
You might be able to get a little bit colder before you froze,
Yeah,
but you'd be dead before you got there.
yeah.
So that's the problem.
You'll see a lot of that in the hospital.
Although, if you live in really northern climates, there is a phrase that they have in ERs, you're not dead till you're warm and dead.
Yeah.
So, let's talk about energy. We're not going to get through this chapter today. We're getting too sidetracked. Sorry. So, identify energy as potential or kinetic and convert it between different units of energy. So, energy, we've already talked about it a little bit. Temperature is a measure of energy, right? It's one of the reasons why I didn't like that oversimplification. It is a measure of energy. Energy is otherwise defined as the ability to do work. Kinetic is energy of motion. Potential energy is from the position or object. I don't have something that is easily droppable, so I'll just say let's pretend for a moment that you hold something up and then let go of it. The amount of energy that it has, the potential kinetic energy that it has, is greater when you hold it higher because there is a greater distance for gravity to have an effect on it as it moves. Therefore, the potential kinetic energy is greater in an object held high than one held low. Where does that potential kinetic energy come from? The fact that you burned a lot of energy to move that object against the force of gravity. Or something else did. But what I just told you was that potential and kinetic energy are interchangeable. You can impart potential energy into an object by exerting kinetic energy into it, which can then be converted back into potential energy if you let go of it, as gravity reactivates it, accelerates it, and it moves down. Creating the always fun game for children to play of dropping a ball on your lower sibling's head. Insert any number of other objects for ball. We all know about potential energy with respect to gravity. This is something that we have seen illustrated to us over and over and over again, proven to us, if you'll forgive the inappropriate use of the P word in a scientific class, over and over and over again in our lives, i.e. the aforementioned game between two young children. And yet the thing is, this potential energy, why does all that water have all that potential energy? Because we spend a whole bunch of energy building this dam to force the water to build up behind it, so that we could take advantage of all of that potential energy of water at an elevated state, so as it flows through this system and possibly through a channel system, we can take advantage of all of that energy to turn a turbine and get some electricity. Or maybe we just made this dam because we were tired of floods. Who knows? But this is potential energy, which can be converted to kinetic energy. There is another form of potential energy, we'll get to in a minute, but I want to mention it here because I'm harping on it so much, and that is potential chemical energy. Give me a metaphor for a dam that uses a plant and has nothing to do with water.
Carbohydrate, sugar.
Sugar. A plant takes carbon dioxide from the air, it takes water from the air, and with the addition of energy from the sun, it turns it into a molecule of sugar that is in no way special or more special than the carbon dioxide or water that it started from. Except for the fact that that new organization of molecules stores some of the energy that that sunlight used to contain. And when you eat that plant, you can break that sugar down into into carbon dioxide and water and capture some of the energy that was released. Every molecule of sugar is literally a tiny chemical battery that stores sunlight just for you by whatever creature or plant it was that you ate in order to get it. That potential energy is just as real as this. And we will do math to prove it. Heat, the energy associated with the motion of particles. Heat is measured by what physical property we have discussed? Temperature, right? The SI unit for energy and work is the joule. That little K behind that big J stands for what? As a prefix? Kilo. So a kilojoule, kilo means 1,000. A kilojoule is 1,000 joules. So you can turn that into a conversion unit, right? Any equality can be turned into a fraction that equals 1. So you could convert between joules and kilojoules. Could you convert between joules and millijoules? Yes. A comparison of energy for various resources that we use. Energy used to sleep for 1 hour, around 10 to the 5th joules. Energy from 1 gallon of gasoline is around 10 to the 8th joules. Seriously, I had you know how you're supposed to get fresh gas every year? So I had it wasn't even 1/3 of a gallon of gas left over from, we had a riding lawnmower. And so I had this gas left over, and so it was coming up on spring, summer, this few years back, and I had this old gas, and I don't know, I don't want to just throw this into my lawnmower because it's probably separated out with the ethanol and stuff, so this is probably not good. So I'll just get rid of it. Well, you shouldn't pour gasoline out; it is bad, contamination. You should properly dispose of your gasoline, or you could use your gasoline for what it was intended for in the first place, which is to just burn it. Well, I didn't have a lot of leaves to burn, so what I did have was a big copper bowl for a fire, like a fire pit bowl, right? And so I was just like, oh, this is neat, so I just poured a little bit just to cover the bottom of the bowl in, and then I knew that this would be dangerous, so I stepped back and took a match and tossed it in there. And you got the effect of whoosh, recorded this on my phone, you got that neat little whoosh, and then it just kept burning for a really long time. You don't realize how much energy is in some of this stuff until you burn it. When I was in high school, I went camping with my parents, and we didn't have any fire starters, so we just used some Doritos. Holy balls! Doritos! You light a Dorito, it will burn for a long time, really bright, and then you realize, I can eat a whole bag of those. And then you realize, why I have such a rotund stomach? Because all that energy that's in that Dorito, that's in you now. Well, not all of it, but a lot of it. Solar energy reaching the Earth in 1 second. 10 to the 17th joules. You ever wonder why solar power is the way of the future? If we could just get good at doing it? Seriously, we suck at solar power. Plants are 10 times better than us. They've also been around for millions of years longer than us, so you would hope that they are. But still, if we could capture a fraction of this, leave your lights on all night, it doesn't matter. The sun will make more tomorrow.
Our biggest problem is not capturing the energy, it's storing it.
It's both. But yes, if we had better storage things in our technology would be good. But still, we are a fraction. The amount of energy capture that we get from, let's call it the average solar cells, is still a fraction of what a tree does. Photosynthesis is an incredibly efficient, and even that only gets a fraction of the amount of energy that touches it. Most of the sunlight that a tree absorbs, it absorbs as just heat. It just warms the tree up, just like it does when you stand out in the sun. But still, plants are so much better than we are. Energy consumption for 1 year in the United States, 10 to the 20. So do the math here for a second. All of the energy used in the United States is 10 to the 20th in joules. How many seconds would it take if we could capture 100% of the energy that hits the Earth from the sun, which we shouldn't do because then the Earth would get really cold really fast. But if we could, how many seconds would it take to power the entire US for a year? 1,000. 20 minus 17. 10 to the 3. Seconds. That much sunlight would power the US for a full year. If we could capture it all. What's this number up here at the top? The energy radiated from the sun every second. Why is that? Because the Earth is really tiny. How much of the light that's emitted from the sun actually hits the Earth? You could actually do the math and answer that question. But the answer is not very much. We're really tiny, we're really far away. Most of the light that the sun emits goes everywhere other than at us. And we're worried about carbon footprints. We should be worried about carbon footprints, but I'm just saying. This is small potatoes. One calorie. That's a term you guys are probably more familiar with, right? 1 calorie? That's 4.184 joules. It's an exact number. A kilocalorie. That, by the way, is when you talk about calories on your food, that's what those are. Do not confuse the calories on your food labels with the calories that we talk about in here. A calorie, you haven't defined that yet. Yeah, we did, right here. A calorie is defined as the amount of energy needed to raise the temperature of 1 gram of water, otherwise known as 1 cubic centimeter, by 1 degree Celsius. So what would a kilocalorie do? It would either raise that 1 gram of water by 1,000 calories, which it actually wouldn't because of conversion, but we'll talk about that in a minute. But what it could do is raise a liter of water 1 degree Celsius. Let's do a little bit of math, just in case I haven't, guilted myself enough about my bad diet. This bottle of Powerade has 1 serving, 130 calories per serving. That's 130 kilocalories. That means that the sugar in this bottle of Powerade would be enough to take a liter of water from 0 degrees Celsius to 100 degrees Celsius and have a lot of energy left over to spare. A lot of energy. Measure out a liter, put it on your stove, turn on your stove and see how long it takes to boil. That's what's in this bottle of water, Powerade. This is Mountain Dew, it'd be even worse. And I keep drinking it. So here's our conversion factors from calories to joules. So we can do some math with that later if we needed to. 1 hour of swimming, depending upon who you are, I imagine, uses around 2,100 kilojoules of energy. So the learning goal here for 3.5 is to use energy values to calculate the kilocalories or kilojoules for a food unit. How do we do that? Pretty much just did. just without specific mass. Carbohydrates are our primary fuel source. If we can, as mammals, we will burn carbohydrates preferentially to either proteins or lipids. In fact, we are so bad at burning lipids that before we burn those lipids, we will convert them to carbohydrates, which is stupid. But we didn't evolve to burn lipids. We evolved to burn carbohydrates. There is a bird. It's a finch. So it's not a big bird. Next time you're at a gas station, pick up a king-size Snickers. And look at how many grams of fat there are in that king-size Snickers. There is a bird. It's a finch, so it's a small bird. But it flies non-stop from Maine and northern Canada over the Atlantic Ocean to Brazil on one king-size Snickers bar worth of fat.
Unladen?
An unladen bird, yes. Aside from the ladenness of all of that fat that it's carrying to burn. But still, that's nuts! It's a lot of energy. Non-stop. There's no like layover in the Seychelles or something. They don't stop in Cuba for a little while. Just all the way down. They do that twice a year. I don't understand birds. Carbohydrates are our primary fuels. Next is fats. Last is proteins. So when we look at our food labels, we have our calories up here, which is actually a kilocalorie, otherwise known as a calorie with a big C. You're looking at your food labels. So 1 calorie is 4.184 joules, right? So 1 kilocalorie is exactly the same number of kilojoules. Remember when we talked about straight conversions before? Grams per mil is the same as kilograms per liter, right? We just add a prefix to both, it stays the same. So 1 kilocal is 4.184 kilojoules. So 1,000 calories, 4,184 joules. Right? How do we figure that out? A relatively complex process that pretty much involves doing exactly what I just told you I did in high school with the Dorito, except somehow capturing all of that heat. We take a portion of the food that we have, we put it inside a container with some wires to ignite it, with an oxygen to burn. We burn it as much as we possibly can until it's completely burnt out, and then we measure how much it changes the temperature of a known volume of water around it. Because that's what a calorie is, right? The amount of energy it takes to change the temperature of 1 gram of water by 1 degree Celsius.
I always wondered, does the food have to be completely dehydrated?
I don't think it usually is, but it's burned to an extent with impure oxygen that it pretty much carbonizes everything. So the water itself isn't going to burn, but it's also not going to add to, it's not going to be fuel for burning type of thing. So it's a good question, but you have to ask a person who does this. But I don't think so. Carbohydrates have 4 kilocalories per gram. Fat has 9 kilocalories per gram. Protein also only has about 4. This is only one significant digit here for our kilocalories. Fat has a lot more energy. It is much more energy dense than carbohydrates. Once again, birds can burn fat directly. They get access to that full 9 kilocalories per gram. When we do it, we take that fat and we, for the most part, break it back down into carbohydrates, spending energy to do so, so that we can burn carbohydrates.
Keep our brain alive.
What's that?
Keep our brain alive.
Yes. Well, depending upon when it is that you're talking about this, yeah. The brain is...
2 days in when you're fully into metabolism.
The brain is the most... Second to the heart, I think, is the most energetically costly organ in your body.
You can actually starve if you eat between 100 and 800 calories. So people get into trouble doing juice fasts
Mhm.
because they do vegetable juice, and they're over 100, so they don't go into metabolism, but they're under the necessary amount to feed your brain, so your brain actually starves.
Because it doesn't actually kick into remetabolizing fat into carbohydrates.
The ketones, yeah.
Yeah, ketone, yeah. Yep. So, we can do a little bit of math to calculate the energy type for a food when its mass is known, right? So here we have the amount of carbohydrates, fat, and protein in all of these potential sources of food. If you knew how many grams of carbohydrates, how many grams of fat, and how many grams of protein you had, could you calculate how many kilocalories there were in that parcel of food? Could you tell me how much energy is in 1 cup of carrots? 11 carbohydrates per gram. How many kilocalories per gram of carbohydrates? 4.
Is that including fiber?
We can digest fiber. So it's the available energy to us. But that's actually a good question because fiber would still burn in a calorimeter. So I don't know. 0 fat, so that makes that math easy. 2 grams of protein per cup of carrots. How many kilocalories per gram is there in protein? Same as carbohydrates from that table, right? Just 4. Would you be able to do that math? Okay, just checking. Losing and gaining weight. The number of kilocalories or kilojoules needed in a daily diet of an adult depends on the gender, age, and level of physical activity. Generally speaking, you will lose weight when your food intake is less than the energy output. This is one of the reasons why men have an easier time losing weight than women do. Because by and large, we have more muscle mass. I say by and large because any given particular comparison, it wouldn't be hard to find a guy who had very little muscle mass compared to a woman who did, right? Compare Serena Williams to I don't care who. Well, most. But still, on average, muscle is expensive. Just sitting there. Let's say that you stayed exactly who you were and changed nothing else about your diet, but somehow I magically add 30 pounds of muscle in appropriate fashion to your frame in some manner. You will burn more calories sitting in that chair listening to me ramble on for 3 hours than you did before. Because just maintaining that muscle costs energy. You lose weight when your food intake is less than your energy output, in general. But here's the thing. It is really easy to eat way more than your energy output. Because food is, especially bad food, is relatively inexpensive. Easy to get. And unfortunately, we're addicted to sugar, which is a totally other biological thing that I don't have time to talk about. Moderately active versus highly active, females versus males. A highly active male in 19 to 30 should get, or should use typically around 3,000 kilocalories per day. Think about that for a second. Let's take a moderately active, young-ish female. 2,100 kilocalories per day. Put that in terms of boiling water. How many liters of water could you take from 0 degrees Celsius to 100 degrees Celsius? Which I should remind you does not actually make it boil. In 2,100 calories, 2,100 kilocalories. Each one of those kilocalories is enough energy to raise a liter of water 1 degree Celsius. That's what a kilocalorie is. Ladies, you guys just sitting here, falling into that 19 to 30 category in a moderately active state, which is making some assumptions. 2,100 kilocalories a day. Just being you, as a moderately active person, is enough to raise 21 liters, right? Because each one of those is enough to raise 1 liter, 1 degree. That's what a kilocalorie is. So 2,100 divided by 100, what is that? 21. You just being you burns enough energy to raise 21 liters from 0 degrees Celsius to 100 degrees Celsius in a day. That's how much energy it takes to be you. You guys ever looked up what The Rock does in a day? He has like 6 meals, has, I think it's over 6,000 calories. And then what he does for his workout is enough to burn through all of that in a day. Add on the fact that he has a lot of muscle mass to pay for in the first place, of course.
People training for the Iditarod will eat beaver fat. It's the most calorically dense
Yep.
food stuff.
Yep.
And they use it all.
Oh yeah, come back emaciated. All right. Specific heat. Specific heat is another one of those things that water is surprisingly good at. It's another property of water, similar to the density of water as it cools off, but why frozen water floats, the mechanism of which we have yet to discuss, but we will. Water also has a very high specific heat relative to most other common things. When does the public pool open? It's usually Memorial Day. A lot of people like to go swimming on Memorial Day. Anybody ever done that? Gone to a public pool on Memorial Day?
It's freezing.
It's freaking freezing! The water's cold! Even if you've had a week of warm weather beforehand, that pool water is going to be cold. You could walk out there and the sidewalk could burn your feet, and you get in the water and you're like, that's cold! Get back out. Stand on the foot burning sidewalk. Splash some water on it, cool it off. Why? Because water has a very high specific heat. Specific heat is different for different substances, but it is conceptually the amount of heat it takes to raise the temperature of that substance by 1 degree. Hold on. Where have I heard that before? What do we call a calorie? The amount of heat it takes to raise a gram of water by 1 degree Celsius. What's the specific heat of an object? The amount of heat needed to raise the temperature of exactly 1 gram of that substance by exactly 1 degree C. This does not mean that calories equal specific heat, except that a calorie is a measure of the specific heat of water, specifically. Which is why, when we do this calculation for water, what do you think the specific heat of water is going to be? Because the calculation is 1 calorie to raise 1 gram. So what is it? 1 calorie per gram? Or 4.184 joules per gram. So what's the specific heat of 24.8 grams of a metal if it absorbs 275 joules of energy? And the temperature rises from 20.2 to 24.5. Let's work this out. We have the time to do it, and we haven't done much math. We've talked about doing math so far tonight, but we haven't done much math. So let's do some math. So what do we have? 24.8 grams of metal, right? It absorbs 275 joules. And the temperature rises from 20.2 to 24.5. What's the first thing we need to do? Before I advance to the slide that tells you, what's the first thing we need to do? We know what we have now. What do we need? The answer is specific heat, right? Now, to make this easy, we can keep this in terms of joules, or we can do it in calories. But what is specific heat? The amount of heat, otherwise known as energy, needed to raise the temperature of 1 gram by exactly 1 degree. So, what is that? It's energy over gram degrees C. That's our unit for specific heat. Everybody follow? Energy in either calories or joules over 1 gram per 1 degree, right? Heat over mass times the change in temperature. So what do we have here? What do we have? What have we been given? We've been given mass, right? 24.8 grams. Have we been given heat? Heat is just energy. So do we have an energy reading here somewhere? 275 joules, right? So what do we still need? Change in temperature. So what's our change in temperature? 24.5 minus 20.2. So, if we take 275 joules and divide it by 24.8 grams times 4.3 degrees C, what's that going to be? We could either do it or we could just advance here and see what it is. So have we done all of this so far? We've done this, right? If you want to plug it in, if somebody wants to plug it in, I'll wait and we'll write it down. So what is this? What is the book telling us to do? We write down the givens. 24.8 grams of metal. That's our mass, right? 275 degree joules of energy. 275 joules of energy. The initial and final temperature. We need the specific heat, and so we have to connect all of these terms. So the first thing they're doing here, calculating delta T. Calculating the change of temperature, right? Which we just did right here, right? 24.5 minus 20.2. That was our 4.3 degrees C. We seem to be doing everything right so far? So, specific heat, abbreviated capital SH, is heat over mass times delta T. 275 over 24.8 times 4.3. Why is the answer given here only in 2.6 joules? Because what's our smallest significant unit here, significant figures? 4.3 only has 2 significant figures, so our answer should only have 2 significant figures. And so if you do the math, it rounds off to 2 significant figures at 2.6 joules per degree Celsius. Now, before I advance this slide, tell me, is that high or low? I ask you this question because I want you to appreciate something. You're on a beach in June. What's warmer? I said, you're on a beach in June at 3 o'clock in the afternoon. What forgive me, we're in Missouri. We don't have beaches here. We have things that pretend to be beaches.
Don't forget Osage Beach.
We have things that pretend to be beaches.
Not even close.
What's warmer, the water or the sand? Sand. Where is the energy coming from that heats both the water and the sand throughout the course of the day? The sun. Is it applying the same amount of energy to the water and the sand? On a per surface area unit, yes. So what is heating faster? The sand. Does that mean it has a high specific heat or a low specific heat? Low. Why? It takes less energy to get that same temperature change. Or the same energy gives you a larger temperature change, right? So, that is in joules. 2.6 joules. Ouch. So now here's some math that this is not telling you how to do. Do it for me. Is the specific heat of this unknown metal more or less than water? You should be able to answer that question right now without doing any math at all. Why? It would require you to remember one little conversion factor though. Let me back up to it. This is specific heat in terms of what unit? If I were to write this out, what was it, like 2.6? 2.6, right, was the answer? But what are the units that I would have? I want to crawl into this space right here. What are the units that I would have? 2.6 what? Joules over grams degrees Celsius. Why am I writing all of those things out? Because when I did this math, there was nothing here that would let me cancel it out, right? If there had been mass on the top, 14 grams, then I could cross out that gram and cross out that gram, and it would just be joules over degrees Celsius. But that guy wasn't there. This is not there. We have nothing to cancel out any of these units, and so we keep all of those units, right? This is just algebra. If it was x, y, and z, we'd still have x, y, and z, right? So, 2.6 joules per gram Celsius. What is the specific heat for water in joules per gram Celsius? 4.184. So is this lower or higher? This is lower. Okay, it's lower. So, now, think about this for a second. Does that mean it would heat up faster or slower than water? Faster. Just like the sand. Question?
Are we ignoring all the trap data?
What trap? What do you mean?
There's space between the grains and sand. Wasn't there. It's not moving. It's highly unfluid.
Very high surface area, allowing for a whole bunch of convection for loss of heat? Sure. But that's also getting a lot more complex than we would need to. Because theoretically, the water would also be giving convecting away a lot of heat every time it rolls over. It would be increasing the surface area of the water from every time it has a wave that comes through. Like there's a lot of different things where we lose. And so we have to keep it simple, conceptually. All right. Does everyone understand what we just did? Specific heat is one of those conceptual things that it's easy to get backwards. It's easy to misunderstand what this is. Specific heat is a measure of how much energy it takes to warm something up, to raise its temperature, right? Our standard bearer much like a lot of the other physical properties that we've talked about so far, is what? Water. How do we measure what a degree Celsius is? A change in temperature of 1 gram of water. How do we measure what volume is? Based on a specific unit of an amount of water under specific pressure, right? Water is this standard bearer for a lot of the things. We use it as the benchmark for a lot of things. Water has a specific heat of 1 calorie per gram per degree Celsius. If your specific heat is less than that, then that means that the same amount of heat will give you, the same amount of energy will give you a bigger temperature change. Let's put this in different terms. Let's put a little bit of water in a pan on your stove. And put a little bit of something else in another pan on your stove. And let's set the stove, both of these burners, to be exactly the same temperature. What is going to warm up faster? The oven is warming both of these pans with exactly the same input of heat, right? What is going to warm up faster? If your specific heat of pan B is less than water, if the value is less than water, then you will warm up faster than water. If your specific heat is higher than water, then you will warm up slower than water. High specific heat means that you have the ability to absorb a lot of energy without a commensurate change in temperature. But it works both ways. That water that takes a really long time to warm up in the morning at the pool or the lake or the beach. Anybody ever gone night swimming before? In the heat of the summer, that beach can get cold. But suddenly that water is nice and warm. Why?
It takes more energy. It retains the heat better because it is a higher.
That beach heated up really fast, right? But that also means it's going to cool off really fast. That water took a long time to heat up. But that also means it's going to take it a long time to cool down. How much energy would be released by cooling 28.4 or 24.8 grams of metal from 24.5 degrees Celsius to 20.2 degrees Celsius? Could you do that math? If I told you that the specific heat of this metal was 2.6 joules per gram Celsius, could you do that math? Because you already have the answer right there. 275 joules. Specific heat is a property of matter. Different matter has different specific heats. Water is very specific. Ethanol has a different specific heat. In fact, let's get past our example and take a look at some. Here's water. 1 calorie per gram degree Celsius. Look at all of these things that are less than 1, which means all of them would do what? Warm up faster or slower than water? Faster. Pretty much everything on this, literally everything on this table, has a specific heat that is lower than water. Including our mysterious metal, right? But once again, don't get confused by the 2.6 because that 2.6 is on which of these scales? Our 2.6 that we got from that equation is in the right-hand column. These are exactly the same numbers. They are equivalent numbers. It's just instead of calories on the top, we have joules on the top, right? But they're just as interchangeable as a kilogram is to a pound or an ounce, right? And this math works both ways. The amount of energy it takes to warm up an object is exactly the same as the amount of energy that you would get if that object cooled back down. Now I'm sort of lying to you here because in a really complex system we'd also have to take into account entropy and where you're losing it to and all sorts of other jazz, but we're not going to worry about that yet. Coastal cities tend to have more temperate climates. I say tend, but you can find a nice coastal city off northern Greenland, and maybe this doesn't really apply. But coastal cities tend to have more temperate climates. Their temperature change tends to be more evened out than inland landlocked areas like Missouri. Why? Because during the day, all that water is absorbing a lot of heat instead of heating up the city. And at night, what's all that water doing? Letting go of a lot of that heat. So the city doesn't cool off quite so fast. This is just a whole bunch of ways that you can alternate or exchange the specific heat calculation. It's just algebra. All you have to do is the same thing we've done before. Take what we know, decide what we need, figure out what it takes to get there. What would be the extra step? If this was a If this was a fill-in-the-blank or multiple choice question on, say, homework or an exam, but the answers weren't in joules, the answers were in calories, what would you have to do? Take 2.6 and multiply it times a conversion factor that converts joules into calories. So you'd have 1 calorie on top is equivalent to 4.182, something like 4.186, something like that. Joules. The joules would cancel out, and you'd be left with calories. And what would that be? 2.6 divided by 4.1 something, mean we'd have a specific heat in terms of calories of around what? 0.56 something maybe? So where would our metal fall? Pretty good, actually. Better than aluminum, right? Better than all of these metals. Look at this guy. Copper, 0.092. Silver's even better, 0.0562. Got gold, 0.0308. What did I mention at the beginning of class? Heating. What could you do if you wrapped $1 around copper? Dollar wouldn't burn. Why not? Because the heat that it takes to actually burn that dollar bill, it wouldn't stick around in the dollar bill, would it? That copper would suck it away. Why? Now you can tell me. Why? Because copper has such a low specific heat. It takes very little energy to raise the temperature of copper. It's going to absorb that temperature, that energy very, very quickly. But what would happen if you kept that copper tube with the dollar wrapped around it inside that candle for a little bit? Eventually that copper is going to get hot. And then the dollar bill is going to start to burn. Right? Let's do it one more time. I'm seeing some I'm getting it faces. I'm also seeing some I'm not sure if I'm getting it faces. So, using the heat equation, let's calculate the energy in kilojoules needed to heat 255 grams of copper from 24 degrees Celsius to 185 degrees Celsius. All right, what do we know? We know mass, right? 255 grams of copper. All right? We are heating, so temperature initial is 24 degrees C, temperature final is 185. So what's our delta T? 161 degrees C, right? Let's keep our units because those might be important, and by might I mean are. So that's what we have. Our equation is specific heat is equal to energy over mass times delta T, right? Let's back up and make sure we're right. Heat or energy over mass times delta T. Yep. So, right now, what do we have? We have, this is what we want, right? Specific heat. That's our unknown. Isn't it? Or am I wrong? What do we have over here? We have mass. We have delta T. This is actually our unknown, isn't it? The question is asking for energy. But we don't know the specific heat either, do we? Or do we? Can we look it up?
Since it's a 0.385, is that what it is? Since it's copper?
0.385 would be in joules per gram Celsius. But our question asked for something very specific, didn't it? It asks in kilojoules. So yes, we should use this one, not this one. Because if we use the calorie one, what would we have to do? Just convert it to joules later, right? So we'll use the joules one. Where's our copper? 0.385. So, specific heat. This is a known now, right? It doesn't tell us this in the question, but we have a resource to look it up. So the specific heat for copper in joules per gram Celsius is 0.385. Can we solve this now? We have 1, 2, 3, 4 variables, right? We have 1, 2, 3 of them as known, right? This one is known, this one is known, this one is now known. So if we plug that in, first off, what are we solving for here? Energy, right? So before we start plugging in numbers, let's do a little algebra. What do we got to do? We have to move our mass and our delta T over to the other side, right? We have to get them out of the denominator because we want energy by itself on one side. So energy is equal to specific heat times mass times delta T. Everybody follow that? So now we can plug in these numbers. 0.385 times our mass, which is 255 grams, times our delta T, which is 161 degrees C. I'm going to move this over for just a second because I want you to see something. Our specific heat of copper is 0.385, right? But that's not what we should write down. What should we write down? To make sure we're doing this right. No, we can put 0.385 because that's a given number. It's an exact number for something that we have from that table. But we have not yet written down units. What's the units for specific heat? Joules over grams degrees Celsius, right? Why did I write that down? Because this is a way for us to double check that we're doing this correctly. We now have grams and degrees Celsius in the denominator. But this is all over 1 and this is over 1. So what can I do with this gram and that gram? They cancel out, right? The 255 stays there, that's fine, but my g's go away. What can I do with that degree C above and that degree C down below? They cancel out. The 161 stays the same. So what am I left with? What unit will my answer already have? Joules. And what is my answer? What does my answer need to be? It needs to be in joules, right? Specifically kilojoules, yes. So if we wanted to, could we do that math now? What would we need to add to turn joules into kilojoules? So what's our conversion for joules to kilojoules? 1 joule is 1,000 kilojoules, right? But we need the kilojoules on the top, because that's the answer we want, right? So, how many kilojoules in 1 joule?
1,000.
Careful.
Oh,
Oh, how many?
How many kilojoules in 1 joule? So, or we could keep it the same way. 1 kilojoule is how many joules? There, that works. Or what's another way you could have written it?
1,000 joules over 1 kilojoule.
You could have put 1,000 joules over 1 kilojoule, yes, but what would that do? If we did it that way, I'm leading you, but that's
Well, yeah, you would be able to.
right. So if we did 1,000 joules up here, that would leave us with joules squared over kilojoules, and that wouldn't be good. That's not what we want, right? So we could write this as 1 joule over, 1 kilojoule over 1,000 joules. And that is perhaps where I should stop, because that is exactly what we have learned so far to do, right? Right? That equivalency. Okay? Could I also write this? If you look at that up there and you go, wait, what? And your mind kind of breaks, just pretend it's not there. How did I get that number up there?
So if you divide by 1,000.
Yeah, I just divided both numbers by 1,000. So 1 kilojoule per 1,000 joules. Over 1,000 joules divided by, do you see that? Let me get out of the way. I'm writing because it's convenient, but this is probably where no one can see it. I should be doing this over here. Question?
5 is 1, J?
1,000 J over 1,000.
0 point, like 0.001. I'm just trying to read that. Okay, I'm sorry.
No, that's fine. That's the problem with writing on the board. If you can't see what my things like, half of the point of this discussion is just that you can see these labels, right? So it's good that you clarify to make sure. I don't want to confuse you. So you could write this, because all that's doing is dividing by 1,000, which is exactly what this is going to do, right? Divide by 1,000. So let's forget about that for a second. I'm just showing you that there's more than one way to skin a cat. It's all just algebra. As long as you do it the right way, it's all right. It's all good. So what's going to happen here? Now this joule and this joule cancel out, right? And so our answer is going to be in kilojoules. So this right here is an exact equivalency. 1 kilojoules over 1,000 joules. So it does not affect our significant figures at all, right? Because it's an exact equivalency. Otherwise, we'd be in trouble, right? Because that 1 kilojoule would tell us we can only have one significant figure. Right? But it's an exact equivalency, so it doesn't matter. So what do we have here? How many significant figures here? 3, because that first 0 doesn't count because it's just holding the decimal, right? So there's 3 significant figures here. How many significant figures in 255? 3. 161? And we just said that none of these mattered, right? Because it's an exact equivalency. So what should our answer be? 3 significant figures. Somebody want to do that math? Because I don't have like calculator in my head.
I got 8.8. I
15.8? And that would be what? Kilojoules?
Oh,
Are we all agreeing 15.8?
yeah, she pointed out to me it's on the next page.
Oh, yes. Which is why, it is, yes, you are correct. Which is why I have not advanced to the next few pages. 15.8. So if any of you were cheating when you looked forward, we didn't cheat up here, right? I wasn't looking at these slides. If you followed along without looking at the slides, then did we all get there? Do we all understand it?
Homogeneous alloy, would it behave like you would expect it to behave? Or like I would expect?
I honestly don't know. A homogeneous alloy, I would expect, would need its own defined specific heat. Because the problem is, you could say, well, a homogeneous alloy of exactly half this and exactly half that, you could probably calculate the specific heat. But the problem with a homogeneous alloy is that that guy's brass from that foundry and that guy's brass from that foundry are probably going to be almost exactly the same, but maybe not exactly the same.
Cooled with different matrices.
Or literally just a percentage different amount of this versus that.
I'm confused about how you got 15.8. Is it just that round the decimal place? Because every time I calculate it, I get like 15,806.
Let's try.
Divide by 1,000 at the end.
Okay.
Yeah.
Alright.
Right, so your answer was in joules, which is correct. Like, that's the first step, yes. But because this is just math and we understand what we're doing, you can put this equivalency here and plug it in right into your thing so that your answer comes out in kilojoules. But yes, if you were getting 15,800 or something that would round to that, then yes, you just divide by 1,000 and that gives you your answer in kilojoules instead of joules. By the way, somebody tell me, this is going back to chapter 1 and chapter 2, and because we have time, somebody tell me, what would this number be in scientific notation in joules maintaining degrees of significant figures?
1.58 times, is that what you're asking?
Yes, 1.58 times 10 to the
10 to the
what?
Well, no.
First off, if we need this in joules, what would it be again? Not 15.8 kilojoules, but what?
15,800 blah, blah, blah.
All right, now turn that into scientific notation.
Well, 1.58 times,
10 to the 4th, sorry.
yeah.
1, 2, 3, 4.
My defense.
It's really far away, it's okay. And I'm not writing really big. This is not like see from the back of the room size font, really, right here. Like I said, that's throwback to chapter 1 and chapter 2. Not in sort of chapter 2, converting it back to joules is sort of chapter 2.
So what was your original question, just so I...
What would this be in scientific notation as joules,
Joules, okay.
maintaining significant figures? Because 15.8, like, it would turn into 1.58, not 1.6.
So what if you would have asked, what is this in significant figures, or what is this in scientific notation in kilojoules?
Then it would become 1.58 times 10 to the 2. Yeah.
Would it be 2 or is it 1? Because that's going to be 1 over.
Well, the problem with 10, yeah,
Just don't ask that. How's that sound?
yeah, it would be 10 to the 1, wouldn't it? Yeah, times 10. Yeah, 10 to the 1.
Okay.
Yeah. 1.58 times 10 to the 1.
Okay.
Yeah, that screws with me because you never, like, something that small you don't put in scientific notation, so you don't think about 10 to the 1 very often. All right, so. Oh, shoot, we have a lot. Was that? No, we're this chapter? Where are they? Where am I?
Change of state,
You just say
Yeah, 3.7.
right there.
Yeah, okay. 63 of 82? More than I thought. But still, from the number of odd looks I was getting, I feel like we needed to maybe focus on this for a while. Do we need to take a break?
Can you just power through?
Power through? Everybody cool with that? Powering through? Good. Because I'd really like to not have to deal with 10 pages of this chapter at the beginning of class on Tuesday. All right, so change of state. This is going to involve some more math because here's the thing. There's a reason why when I've been talking about calories and diet and everything, and I've said, okay, how much does it take to raise, it's enough energy to raise water from 0 degrees to 100 degrees. Because, and I didn't just say boil, you can raise it from 0 to 100, that's fine, that's straight, that's easy math, right? But going from 100 degrees to 101? Can you have liquid water at 101 degrees?
Well, what degree Celsius?
Celsius, yes. Good question.
Would be boiling, right?
It would be beyond boiling at 101.
Well, I guess it'd be.
It would already be boiled. Unless, of course, you're talking about water under higher pressure, in which case you're breaking the question. Because yes, you can get water at above 100 degrees. In the same way you can get water below 0 that's still liquid, but not under normal conditions. So, to get to 101 degrees, the water has to boil. It has to become a gas. And changing from a liquid to a gas requires energy. So that jump from 100 to 101 is a lot more energy than the jump from 99 to 100. Everybody follow? And the same thing happens at the melting point. Going from -1 degree Celsius to 0, and then turning into a liquid, that change of state from solid to liquid takes a lot more energy than simply bringing water to 0 degrees, warming it up a little bit. A change of state. A state is this a physical or chemical change? Everybody agree? Physical change. Water is still water, regardless if it's liquid or solid, right? So this is a physical change, not a chemical change. To go from one state to another requires a lot of energy. So, the melting point of water is the same thing as the freezing point of water. Where does water melt?
Surface.
At its surface, at 0 degrees. If water at its surface is at -15 degrees, is it melting? No, it's still at -15 degrees. You add heat to it, it's just going to get a little bit warmer. Now it's -13 degrees, -10 degrees, right? It's warming up. It melts when it reaches 0 degrees. So what is the only temperature where you can have water as both a solid and a liquid under normal conditions? Right at 0. In the same way that you can have water that's 100 degrees as both a liquid and a gas. Not at the same time.
Okay.
This molecule is a gas, this molecule is a liquid, right? It's not like one atom can simultaneously exist as both. I don't mean to confuse you in that manner. But some of the liquid, some of the water at 0 degrees can be solid, and some of the water at 0 degrees can be liquid.
This is why you get like slush.
Yes.
It's a process.
Right, that perfect moment, right at 0. Because here's the thing. Have you ever noticed when you're boiling water that you don't, sometimes you get a hot spot, and that's cheating, I'm not talking about that, but when you boil water, what's the process? You put water on the stove, you let it heat up, blah, 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 you start seeing little bubbles forming on the bottom, but when it finally starts boiling, it just kind of goes, right? It doesn't boil just at the surface. It doesn't boil just on the edges. It's going to boil where the heat is being added, which unfortunately in this metaphor is the bottom, but it's boiling everywhere. You don't get like the left side of the pan boils and the right side of the pan doesn't, unless your pan is lopsided. But point is that we're getting heat everywhere. It has to heat up everything. All of that water has to be at 100 degrees before it will actually boil. Because if there is any that is not, if you add a little bit of even warm but not boiling water to water that's about to boil, what happens? Next time you're doing this, do a little experiment at home. Take some, don't use cold water because splashing is bad, but take some, warm water from your tap. Get your water, you're making mac and cheese for your kids, whatever, warm it up, cooking some pasta. Wait until it's right at that point where it's about to really start boiling, right? Like you're seeing the bubbles on the bottom, and it's like a few of them are starting to rise. Take that bit of water, just pour it right in there. All those bubbles, gone. Why? Because all the heat that all the water that was already there had, when it came in contact with water that wasn't that hot yet, what did it do? It donated some of that heat to the not quite as hot water, which means all of the water isn't right at 100 degrees anymore. Now it's a little bit lower. At 0 degrees, you can have both solid ice and liquid water. And you will not have all liquid or all solid until it is all liquid or all solid. None of that 0 degrees liquid is going to warm up to 5 degrees until all of the ice is melted. If you're cooling it off to freeze it in your freezer, none of that ice will drop below 0 until all of the liquid has frozen. Because it is always going to give or have energy donated to it. The cold thing will always get energy donated to it from the warm thing until everyone is the same temperature. The melting and freezing points are the same thing. We can be both at the same time in one big conglomerate pot, right? But once again, not the same atom. The heat of fusion, which is perhaps poorly named, because when I think of fusion, I think of stellar phenomenon. I think of fusion of molecules. Really what we're talking about a heat of fusion here is, we're talking about the fusion of otherwise liquid molecules fusing together to form a solid. And what is a solid? It has defined shape, right? So we're fusing into a chunk of ice in the case of water, instead of liquid water that just flows. The heat of fusion is the amount of energy that must be used to convert exactly 1 gram of solid to liquid, or vice versa, at the melting point. And in this case, it's 334 joules. Let me ask you a question. What's the relationship between this and the specific heat of water? What's the specific heat of water in joules? It's 1 calorie per gram degree Celsius, or 4,000 something or other joules per gram degree Celsius, right? So, we're not changing a degree at all here. We can't use the specific heat equation, because there is no temperature change. Delta T is 0. Water that goes from solid to liquid or back is not changing temperature at all. It is changing state. But what is the relationship? Does it take a lot more energy? Or a lot less? 334 joules will convert 1 gram of ice to liquid, or removing that much energy will convert 1 gram of liquid water to ice. The specific heat was 4,000. So it doesn't take a whole bunch of energy. This is less than the specific heat, right? So it doesn't take a whole bunch of energy, but it still takes some, where there is no temperature change at all. And there will be no temperature change until all of the water in question is ready or has gone through that change of state. So, 334 joules or 80 calories, not kilocalories, but 80 calories. That's melting. Why is this the same number? Heat of fusion here, heat of fusion here, okay? So we have quantity, 1 gram, sorry, we moved on something else. This is the same number because this is still just the same amount of energy going back and forth. Here heat is removed to freeze it, here heat is added to melt it. Follow? But it's the same number, 80 calories or 334 joules. 80 calories or 334 joules. It takes exactly the same amount of energy to melt something as it does to freeze something. In the same way that it takes exactly the same amount of energy to heat something up as you get back when you cool it off. Everybody follow? So here are all these conversion factors that we can do. 80 calories per 1 gram or 334 joules per 1 gram. So how much do we have? Times the heat of fusion, that's how much heat we have to gain or lose to convert the whole thing. Do you see a practice problem coming up? How many kilojoules are needed to melt 32 grams of ice at 0 degrees Celsius? How would we do this? I'm not going to spend a lot of time on this because I have a lot of slides to get through, but also because we should be able to do this, right? We just did a whole bunch of things just like it. We just don't have a delta T here. We have mass, right? And we know we're at 0 degrees C. Why is that important? What if this question said how many kilojoules are needed to melt 32 grams of ice at 5 degrees C? Ooh, darn it. I thought I said I was going to do this quickly. What would that change here? What would we have to do first? Before we can melt the water, what do we have to do? Or, this is melting, sorry, at negative 5 degrees C. So what if we have ice that's not at 0? What if you have ice that's not ready to melt? We have to heat it up first. What would we need then? That specific heat equation?
Oh, yeah.
The thing we just talked about, right? And then add on a little bit more energy to actually melt it, right? But let's start with this. We have water, it's ready to melt. We've got 32 grams. 32 grams of ice. We need kilojoules, so there's a little bit of conversion there because our conversion factor before was not in kilojoules, it was in joules. So here we go. Here's our conversions. And here's our math. 32 grams of ice, right, as a solid, that's what that S means, times 334 joules per gram, right, times our conversion factor of a kilojoule per 1,000 joules. This looks really familiar to me. Does it look really familiar to you? Gives us 10.7 kilojoules. That's how much energy it takes to melt 32 grams of ice. That's kind of a lot of energy. So that's melting. There's something called sublimation. Melting is the process of going from a solid to a liquid. But there is a process called sublimation, where particles on the surface of a solid will change directly to a gas without going through the liquid state. But there's no change in temperature. The reverse process is called deposition. Where have you seen sublimation before? Dry ice undergoes sublimation. Sure. So dry ice is a solid, right? And so every other thing that you've ever dealt with in your life, if it's a solid, when it melts, what does it become? A liquid. Don't you find that, you guys ever use dry ice in coolers and stuff? Isn't it so annoying when you've got all that liquid carbon dioxide on the bottom of your cooler? Ever had that problem?
It's fun.
Well, it's because it's not liquid. Dry ice doesn't melt to become a liquid. It melts and becomes immediately a gas. There is no liquid stage in between. That's sublimation. You've seen it somewhere else too. In the winter when we have ice storms, We get ice on trees. And then the next day it never gets above freezing. What happens to the ice on that tree? Give it enough time, it goes away. You ever gotten ice, like those little frozen things on your windows? It's on the edges of your windows? That's deposition. But that can also disappear without actually melting. That's sublimation. An interesting thing, why do we add salt to our driveways when they get icy? It's to help the salt melt, right? Except that, have you ever gone out and looked at that ice as it melts from the salt? Does it turn into running liquid water? Sometimes it does if there's enough of it, but most of the time it just gets brittle and seems to almost just evaporate. Guess what it's doing? It's evaporating. It's sublimating. The ice crystals that you're dropping on that, everybody thinks you're adding ice because it changes the melting point of water and so it'll unfreeze or something. That's not why you're adding salt to your ice. The salt gives the water a matrix to sublimate and become a gas. That's why.
Is this all related to transpiration?
No. Transpiration is something that plants do.
I mean, sorry. You lose material off the surface of water.
That's just sublimation. Yeah. It's this.
Okay.
Yeah. It's sublimation, except you're just giving it a matrix. You're giving it a catalyst to sublimate. Has a lot to do with entropy, and we're not going to get into the math with entropy, but here we go. So, evaporation is when we take a liquid to a gas. Sublimation is when we take a solid to a gas with no change in temperature. You'll note that there's not a big calculation here, right? Because it involves entropy, and we're evidently not involving entropy in this class yet. Be thankful. Entropy is a hard concept to wrap your head around sometimes. Evaporation, I could be wrong, maybe I'm just not remembering correctly about what's here. When we're taking liquid and turning it into a gas. That happens at the boiling point. Once again, all of this water in this beaker right here, it is heated up to 100 degrees Celsius. And then none of that water will get any higher. None of that water is at 102. If you took a chem lab and watched this happen, you could boil all of that water, and guess what would happen to that thermometer right there? It would never go above 100. As all of this water disappeared, all of the heat coming in from that Bunsen burner would be going into the cost of evaporating the water. None of that water would go above 100. It would stay at exactly 100 the entire time. That heat's going somewhere, right? But it's not heating up the water. It's paying for the cost of changing from a liquid to a gas. Now what happened if instead of a big Bunsen burner and a beaker here, what happened if this was actually a really big glass ball? Once all that water turned into water vapor, then what would that Bunsen burner start doing? Then what would happen to that thermometer? It would start climbing again. Because now that we're all a gas, we can start warming up further, right? Condensation is the opposite of vaporization. Condensation is when gaseous water turns into liquid water. You guys ever had like a problem? Oh, I don't know. I guess the easiest way to get this problem outside of like running your car through a flash flooding river is you go to the beach, you go swimming or whatever, you get into your car and everybody's like got blankets, the towels are soaked with water. The next day you get in your car and you notice something. Your car is really humid, right? From all that water, all those towels. What's the best way to clear it out? You want to turn on your heater? Burn all that water away? What's the best way to get rid of all that humidity in your car? Have you done this recently? What's that? Turn on the AC. My house yesterday, because I was really resisting turning on the AC, because I was like, oh, it's just the first hot day. I don't have to turn on the AC. By 8 o'clock at night, my house is at 78 degrees, and it felt like it was a sauna. Like, dude, turn on the AC. 5 minutes, oh, so much better. Why? Because the air conditioner, all those coils that were cooling down and running all that air past to cool down the air, what happens to air with a lot of water in it when that air cools down? The water condenses out of the air. Same thing happens when you got your cup with a lot of ice in it. Gets water droplets on the outside of your cup on a nice hot summer day. That's not because the water on the inside of your cup is spilling out and coating the outside. It's not leaking through the walls of your cup. It's water from the outside air condensing on the surface of your cup.
Could you also just have low surfaces?
What's that?
Could you also have, what's the word, the low surface heat?
Specific heat?
Specific heat, yeah.
You could, except that we can't change the specific heat of water because it's a fundamental property of
I'm
the
saying you as a person.
Hmm.
That's what I feel like as my husband.
Yes, our heat tolerance, that's a totally different thing. That's behavioral. Yes, yes. Heat of vaporization is the amount of heat it takes to change 1 gram of liquid to a gas. Or it's released when we take 1 gram of gas and bring it down to a liquid, right? For water, it's 540 calories or 2,260 joules of heat is needed to convert 1 gram of water into 1 gram of water vapor or steam. This can only happen at 100 degrees. So what takes more energy? Melting water or boiling water? Boiling. Melting took only about 300 joules, right? Boiling takes 2,000 joules per gram. But it makes sense, because it takes a lot of energy to make water stop holding on to each other and really spread out and become a gas. That same 2,000 joules would be released in some manner if you were to cool off a gram of water. We talked about this earlier. Why is it that taking, aside from the fact that it's a drug and you shouldn't do it, why is it taking ecstasy and then going to a rave where you're dancing around a lot's a bad idea?
You can't sweat.
Because you can't sweat and you overheat, you go into heat stroke. Okay? Why does heat stroke, or why does not sweating lead to heat stroke?
So you can't cool down your body.
Because we use sweating as a means of evaporatively cooling our body. Why does that work? How much energy does it take to evaporate water? A lot. So if you put a lot of water on your skin, you think maybe it's got to get that energy from somewhere? Now, I'm not telling you that it takes this much energy to evaporate water off of your skin, because once again, entropy plays a role here. We're not bringing entropy into the equation yet. But conceptually, that is why we sweat. We sweat because evaporating water takes a lot of energy. And if we can find a way to use that energy needed to suck some of that energy from your body, then that will help cool you off. That is also where we get things like, what is the term? Heat index, right? It's going to be 96 degrees tomorrow with a heat index of 108. What's that mean? It means don't be an idiot, don't go outside and get all sweaty. When the humidity is really high, there's no place for the water on your skin to go. It can't evaporate. And so therefore it can't cool you off. This is why 108 degrees or 95 degrees with high humidity feels like 108. That's what that heat index is. You will heat up and react as if it was 108 degrees instead of the 95 that it is, because the humidity is so high that your normal sweating mechanism to cool you off, all it will do is get your shirt wet. And that has everything to do with how much energy it takes to change the state of water. And a few other things too. So here we have heat of vaporization, conversion factors. We can calculate how much heat it takes to do something. Do you feel some math coming? Look at this curve. Down here is heat added. So this is, let's take some water at negative 40 degrees and start adding heat. That temperature is going to rise all the way to 0, but then for a certain amount of time, the temperature will not change. What is happening? We're still adding heat every second, but the temperature is not changing. What is happening instead? Where is that heat going? It's paying for a change of state, right? Then once we're all liquid, we can rise from 0 to 100 in a relative linear line. But then for a significant period of time, we keep adding the same amount of energy, but nothing is happening to our temperature. What is happening? We are paying for the change of state from liquid to gas. And once we're all gas, then we can start raising in temperature again. Could you tell me how much energy that was? Yes. Short answer is a lot. You are correct. But if I said that you've got, say, 50 grams of ice at negative 40 degrees C, how much energy would it take to turn it into 50 grams of gas at 160 degrees C? Could you do that? What would it take? We would need specific heat calculations here, right? Warming it up to 0. Then we would need the heat of fusion calculations to melt it. Then we would need specific heat calculations to raise the temperature to 100. Then we would need the evaporation or the boiling calculations to turn it all into a gas. Then we would need specific heat calculations to raise the temperature of the gas. Could you do all of those things?
Eventually.
Eventually. It would take you a while. But you could do them, right? There's nothing... When you break it down into those steps, we've done all of those things, right? And if you had, say, a relatively unlimited amount of time on a homework assignment, or say a slightly more limited amount of time on an exam, some of that could be done, right? No? It's just too much effort shutting off. The cooling curve, it's exactly the same but in the reverse direction. Why? It's a very simple answer that seems almost counterintuitive. The physical and chemical properties of matter are directly dependent upon the atoms that make them up. And therefore, the amount of energy it takes to go in this direction is exactly the same as the amount of energy you get back going in this direction. It's exactly the same.
Well, but then with this, what's the word? Sublimation or whatever?
Mm-hmm.
How does it skip?
That is a really good question. So how does it go from a solid to a gas with no change in temperature? It's a really good question. And what I will tell you is it takes exactly the same amount of energy.
Okay, so that's what you're talking about right now, is energy.
Right. There's a guy that's hiding behind this graph. And he's like twisting his mustache with an evil grin and laughing maniacally because he has these nefarious plots.
Is this the guy from the Pink Panther? Is that what it is?
No, this guy's called Entropy.
Okay.
But he could be wearing a superhero villain suit if you like. Entropy is a huge part of these calculations.
Oh, so that's what you were talking about earlier.
Yes. It is a huge part of these calculations that we're not going to worry so much about right now.
Thank you.
Because you don't need to get that. And let's put it this way. It's hard enough to really conceptualize how understanding how the specific heat of water is going to impact your day-to-day life as a medical professional. adding in calculations for entropy just makes it almost like arguing about philosophy. It's like, yeah, this is even more pointless. Like, it's a fundamental thing. I don't mean to downplay entropy or badmouth them. Entropy is as important, if not more important, than freaking gravity when it comes to really understanding how some of this stuff works. But we don't need to get that detailed.
I'm totally fine with that.
Okay, good. I thought you might be. Now, that's not to say that he's not going to come in later, but we're not going to worry about him right now.
We don't ever have to invite them if we don't want to.
And that's it. Here I was worried I wasn't going to finish. Are we supposed to go to 8:55? We have 5 minutes. Anybody have any questions about what we went over today? Sorry if that last little bit felt a little rushed. I didn't want to leave anything behind, but like I said, it's all math, but we'd already done it all, right? We've done specific heat calculations. We've done melting calculations. Plus, it didn't actually ask us to do math. I'm pretty sure if we look into those problems, the problem set, there are some questions in there that would walk you through all of that, like doing this first and adding this. I highly suggest you check it out. I'm gonna try and make sure that I get your homework posted so it'll open up tomorrow. It will be due, I guess the easiest way to do it is just make it due before class starts a week from today.
What
So-
time are you gonna open that up tomorrow?
I'll probably set it to open up at 8 o'clock. If I finish it tonight, I'll time it to open up at 8 tomorrow, 8 a.m.
For the questions, for the problem.
Which is what I'll do for the test too.
I won't have kids home.
For like the problem questions that you have as extras and
Right.
the homework, is that similar on what the test will look like?
That is a really good question. So here's what I can tell you for that. I haven't put the test together yet. What I can tell you is there's a difference between the way that the book, because the homework problems are going to either be exactly or very similar to what's in the back of your book. So if you notice, the back of your book, half of those problems have answers, and half of them don't. So your homework is going to come from the half that don't. But that means that there are problems exactly like them that do have answers worked out, so you can practice a little bit. It also means that if you're a really, really motivated student, you could get ahead on your homework and just answer all of the questions at the end of every chapter so that you're just ready to pick that answer and go. I don't expect anybody to do that, but I'm just saying you could if you want to. So the test, on the other hand, is going to be different because what I'm not going to do is go back through and manually grade 48 questions from 10 students, possibly more than 10 students if this is during a regular session when I had more like 20 or 30 students in here. So those questions are going to be similar, but they're probably going to be like true-false questions or multiple choice questions. So you'll still have to do math very similar to those, but it'll be like pick the correct answer out of 4 options. Or it'll be like, for example, do this math, true, false. This would heat up faster than water, right? So like you have to do the math, and then I can ask you a true-false question to determine whether or not you understand the relationship between specific gravity of A and B, right? Questions like that.
But I'm more so, I mean, that's helpful to know, but even on level of difficulty, will they be in line? I only ask because I had a horrible experience with a teacher that put their tests on D2L and take on your own. I think because they thought we couldn't take it on our own, they
made it really, really hard?
Really, really hard.
A really, really hard test is the type of thing we do because A, you can take it anytime you want, and were those timed?
Yes.
They were timed too?
They were terrible.
Yeah, I can see why that might be bad. Like if I was gonna do that, I wouldn't put a time limit on it. Like this is gonna take you 6 hours to finish, but suck it up, you'll have your book, so don't complain. Like I could maybe see that as a mentality, but no, some of the questions will be harder, yes. And unfortunately, because of the nature of a random block test, if you're helping a friend, your question might have 2 or 3 or 4 questions and like, wow, these were kind of like tough.
And your friend's test was like, whoa, mine were all easy. But then the next time you do it, they might get shafted with the hard questions and yours the easy one. So the test bank questions are gonna have some easy questions in them, and they're gonna have some hard questions in them. And it will be random which ones you see. So your test might be a little harder or a little easier than somebody else's, but no, the intention is to make a test that I think a reasonable student would be able to finish in a reasonable amount of time, that being less than 2 hours. So I'm not gonna give you 5 problems that work out 50 grams from -40 to 160, right? But there might be something in there where you're doing a step or two of that, or it might be you're doing the first half and somebody else is doing the last half, and that type of thing. Or if you're really unlucky, one question where you're doing the first half, and another question where you're doing the last half, and then you end up doing it all anyway. But hey, it's 2 of your questions instead of just one.